The critical information arrived at 7:47 a.m. Eastern Time on October 29th, 2025. David Finocchia, a propulsion and guidance engineer at NASA's Jet Propulsion Laboratory, submitted a report that reverberated through every astronomical facility globally. 3I Atlas, the celestial traveler observed for several months, has deviated from its predicted orbital path. It's currently accelerating away from the Sun at a rate of 135 kilometers per second squared, and additionally, a transverse acceleration of 60 kilometers per second squared is noted. While these figures may appear minuscule, they are validated and concrete. If 3 Atlas is indeed a natural comet, it's imperative that it sheds 10% of its total mass within the upcoming 30 days. This translates to an astonishing 5.5 billion tons of material expelling into space, creating a cosmic cloud so immense that it should be visibly blazing across our solar system, observable by every telescope from Earth to Jupiter. However, a perplexing anomaly keeps me awake at 3 o'clock in the morning. What if there's absolutely no evidence of such an eruption? If you're new to this channel, please engage the like button and subscribe. Your support significantly aids our growth. I'd appreciate it if you could share in the comments your location, the current time there, and whether you believe we're witnessing the most significant scientific cover-up in astronomy or the most misunderstood comet in history. The 4 arc-second discrepancy. October 29th was anticipated to be a predictable day, marking perihelion, the closest approach to the Sun. Every comet, asteroid, and celestial body composed of rock and ice that has ever traversed our solar system adheres to a trajectory governed by gravity. The principles of Newtonian physics, refined by Einstein's theories, provide an elegant and precise mathematical framework tested over centuries. By inputting an object's mass, velocity, and position, one can accurately determine its future location, whether it be in an hour, a day, or a month. The universe does not present us with unpredictable orbital paths. It is fundamentally constrained by gravity's deterministic nature, except 3 Atlas deviated by 4 arcseconds from its expected position. 4 arcseconds may seem insignificant, a minuscule fraction of a degree. To visualize, if you were to hold a dime at arm's length, 4 arcseconds would approximate the width of a human hair as seen across a football field. Astronomers routinely work with such minute angular measurements, accustomed to a level of precision that often eludes the average person. However, the crucial factor is that, at a distance of 203 million kilometers from the Sun, a 4 arcsecond deviation translates into a tangible spatial displacement, a measurable shift from the path dictated by gravitational forces. Such an offset can only be attributed to a non-gravitational influence. The Atacama Large Millimeter, Submillimeter Array, or ALMA, a collection of 66 radio telescopes situated in the Chilean desert, first detected this anomaly. Operating in concert, these instruments observe the cosmos at wavelengths imperceptible to the human eye. On October 29th, as 3 Atlas neared its perihelion, ALMA's operators identified an unusual deviation in its positional data. The object was not located where the Jet Propulsion Laboratory's ephemeris predicted, specifically in its right ascension. Although the discrepancy was minor, it remained consistent across multiple observations, prompting David Finocchia, an expert in orbital mechanics and near-Earth object trajectories, to flag it immediately. Finocchia has dedicated his career to charting the courses of asteroids and comets, earning his doctorate in mathematics from the University of Pisa. He has spent years perfecting the models used to predict close encounters, potential impacts, and orbital changes. When he submitted his findings to the JPL Small Body Database, he was not theorizing. He was documenting an observed phenomenon. 2 distinct acceleration components were identified: a radial acceleration directed away from the Sun, and a transverse acceleration perpendicular to the Sun's direction. Both are measurable and necessitate an explanation. For a comet, the expected cause is straightforward. As the icy nucleus warms, volatile compounds like water, carbon dioxide, and carbon monoxide sublimate, transforming directly from solid to gas. These gases are expelled from the surface, carrying along dust and debris. The momentum of this ejected material generates a propulsive force against the nucleus, akin to a reverse rocket engine. This phenomenon, known as the rocket effect, has been observed in hundreds of comets within our solar system and is considered a natural and well-understood process. However, the numerical data presents a startling challenge. The principle of momentum conservation is absolute. If 3 Atlas is accelerating due to outgassing, then the mass of the ejected material multiplied by its velocity must equal the mass of the nucleus multiplied by its change in velocity. This equation can be rearranged to calculate the rate at which the comet is losing mass. Avi's calculations, based on Finocchia's data, yield a brutal result. If the acceleration measured by Finocchia originates from sublimation, then 3 Atlas is effectively evaporating at a rate suggesting a half-life of approximately 6 months. Over the month it took to traverse the perihelion distance, it should have lost at least 1/16th of its total mass. Back in the spring, the James Webb Space Telescope measured 3I Atlas's mass loss rate at a steady 150 kilograms per second for 5 months. This rate was insufficient to produce any detectable non-gravitational acceleration. Based on this observation, Lowe and his team estimated the nucleus's mass to be at least 33 billion tons. This is a colossal object, far exceeding the size of any previously observed interstellar visitor, 1,000,000 times larger than Oumuamua and 1,000 times larger than Borisov. 33 billion tons represents an immense quantity of ice and rock. 1/16th of this mass amounts to 5.5 billion tons. This is 5.5 billion tons of gas and dust that should currently be erupting into the space surrounding 3I Atlas, forming a coma so expansive and brilliant that its visibility would be undeniable. Consider the sheer scale of 5.5 billion tons in space. Envision every structure in New York City, every building, every vehicle, every bridge, every subway tunnel, reduced to powder and propelled into the void at hundreds of meters per second. This is the magnitude of the material we're discussing, a plume that would dwarf the nucleus itself, glowing under solar radiation, scattering photons, and emitting spectral lines from ionized gases. Such a spectacle would be observable even by amateur astronomers from their backyards. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE spacecraft, currently en route to Jupiter, is scheduled to pass within 64 million kilometers of 3 Atlas on November 4th. JUICE is not specifically designed for comet observation. Its mission is to investigate Jupiter's icy moons, search for subsurface oceans, and map magnetic fields and radiation belts. Nevertheless, it is equipped with cameras and spectrometers. If a substantial cloud of gas surrounds 3I Atlas, JUICE is certain to detect it. The observational geometry is ideal, the proximity is sufficient, and the instruments possess the necessary sensitivity. If JUICE observes nothing, if the returned images show a faint, compact nucleus devoid of any significant coma, expanding debris shell, or indication of the catastrophic mass loss demanded by the non-gravitational acceleration, then we face a profound problem, as the numerical data is irrefutable. Either 3I Atlas is expelling material at an obviously detectable rate, or the observed acceleration is not a product of sublimation. Lowe detailed this predicament in his blog post on October 30th. He meticulously presented the calculations, referencing the Webb telescope data and the JPL orbital fit. He avoided ambiguity, stating plainly that if no significant gas cloud is observed in November and December, then the non-gravitational acceleration cannot be attributed to cometary outgassing. If it is not outgassing, then what remains? This is where the discussion becomes uncomfortable for many astronomers. Lowe has encountered a similar situation before with Oumuamua. That first interstellar visitor also exhibited non-gravitational acceleration. However, the Spitzer Space Telescope found no evidence of the expected accompanying gas and dust. Oumuamua accelerated without leaving any discernible trace. To address this, comet experts coined the term dark comet, a comet that doesn't produce a visible coma or tail, but still outgasses sufficiently to alter its trajectory. Lowe has pointed out, with his characteristic directness, that labeling such an object a dark comet is analogous to calling a cave dweller's mobile phone a shiny rock. It's a descriptor that sidesteps the more challenging question. If an object accelerates without producing the supposed cause of that acceleration, perhaps it is not a comet at all. 3 Atlas was expected to be different. It possesses a coma and a tail. Images captured by the Hubble Space Telescope in July depicted a teardrop-shaped cocoon of dust trailing the nucleus. Ground-based telescopes detected spectral signatures of cyanide, nickel, and hydroxyl radicals. It appeared to be a comet. The scientific community breathed a collective sigh of relief, believing that interstellar objects could indeed behave normally, and Oumuamua was an isolated anomaly. 3I Atlas would serve as proof that interstellar comets follow the same physical laws as their solar system counterparts, differing only in their chemical composition due to their formation around different stars. However, the 4 arc-second deviation, the measured acceleration, and the mass loss calculations are now loudly proclaiming that something is fundamentally amiss. We are on the precipice of discovering whether the universe adheres to our current understanding, or if it has been attempting to communicate a different truth that we have been unwilling to acknowledge. November and December will provide the definitive answers. JUICE will commence its observations on November 4th. Ground-based telescopes will have their opportunity as 3I Atlas emerges from behind the Sun in mid-November. Hubble and Webb are also scheduled to observe, along with the entire International Asteroid Warning Network, mobilizing observatories worldwide for an unprecedentedly coordinated tracking effort. They are treating this as a planetary defense exercise, a euphemism for thoroughly understanding the object's nature and behavior. On December 19th, 3 Atlas will achieve its closest approach to Earth, at a distance of 269 million kilometers. While still remote and posing no threat, this proximity will allow every major telescope to obtain a clear view. If a plume exists, it will be visible. If a coma is expanding at the rate indicated by the mass loss, it will be measurable. If spectral lines reveal the chemical fingerprints of significant sublimation, they will be catalogued. And if there is nothing, if 3 Atlas continues its silent journey through space, compact and unassuming, accelerating without any apparent cause, then Avi's question becomes unavoidable. What if the non-gravitational acceleration is not a consequence of heating and sublimation? What if it is intentional? What if an internal mechanism is firing, executing course corrections, and utilizing the Sun's gravity for a precisely calculated orbital maneuver? 4 arc-seconds. That's all it took. 4 arc-seconds transformed October 29th from a routine perihelion passage into the most scrutinized moment in the history of interstellar object studies. 4 arc-seconds prompted every astronomer on the planet to pause and confront the question they had been avoiding since July. What if 3 Atlas is not what we believe it to be? Finocchia's report is publicly accessible. You can find it in the JPL Small Body Database under the designation 3 Atlas. Navigate to the non-gravitational parameters section. They are clearly listed: radial acceleration, transverse acceleration, accompanied by their uncertainties and error bars. the kind of data typically published in peer-reviewed journals, scrutinized by independent teams, and integrated into the permanent scientific record. This is not conjecture. It is not sensationalism. It is navigational data from a highly respected orbital mechanics expert at NASA, stating in the unambiguous language of mathematics that 3i Atlas is not following a purely gravitational trajectory. The central question is not the reality of the acceleration, but its origin. In the coming weeks, we will receive an answer. Either we will observe the plume, and 3 Atlas will be remembered as an exceptionally volatile interstellar comet with extreme sublimation rates and fascinating chemistry, or we will not. If the latter occurs, every assumption we have made about this object, every comforting explanation, every reassuring press release will crumble. Because if an object approximately 5.6 kilometers in diameter can accelerate through space without expelling billions of tons of gas, then it is engaging in an activity for which we currently have no natural explanation, an activity that requires energy, control, and precision, an activity that appears far less like geology and far more like engineering. The clock is ticking. JUICE begins its observational campaign in 6 days. Ground-based telescopes will have their opportunity in 2 weeks. Hubble and Webb are already scheduled for December. The data is imminent, and once it arrives, we will have our answer unequivocally. However, there is a detail that haunts me, a chilling thought that lingers. The timing. 3 Atlas reached perihelion on October 29th. This is the optimal moment for a spacecraft to engage its propulsion system, a phenomenon known as the Oberth effect. When deep within a gravitational well and moving at maximum orbital velocity, any applied thrust is amplified by the existing kinetic energy. This is a fundamental principle of astronautics. To alter a trajectory, whether to increase speed, decrease it, or change direction, the most efficient time is at perihelion, when closest to the Sun. 3i Atlas performed precisely this maneuver, right on schedule and at the mathematically opportune moment. Was it a mere coincidence? Did the ice just happen to sublimate with sufficient force at that exact instant to produce a measurable acceleration during the single most efficient window for such a change? Or did something within that object possess the knowledge and capability to activate its propulsion system at precisely that time? The 4 arcsecond deviation is not merely a measurement. It is a profound question etched into the trajectory of an object that has already defied all our expectations. And the answer, whatever its nature, is hurtling towards us at a velocity of 61 kilometers per second. November 4th. In 6 days, JUICE will reveal what truly lies beyond. And once that revelation occurs, there will be no turning back. No more speculation, no more debate, only data, and whatever that data discloses about the nature of the third interstellar visitor to cross our threshold. Bluer than the sun. On October 30th, coronagraphs captured something impossible. Multiple spacecraft, positioned at various points throughout the solar system, collectively recorded the same anomaly. During its perihelion passage, 3 Atlas shifted its color spectrum towards wavelengths bluer than the sun itself. This was not a subtle difference. It was a distinct, measurable, and inexplicable blueness. Such an occurrence is unprecedented for any natural comet ever observed by humanity. Within hours of processing the data, Qichang Zhang and K.L. Batams published their findings. Their paper, submitted to the Astrophysical Journal Letters, includes photometric data from 4 independent instruments: Stereo's Secchi cameras, specifically the HI-1 heliospheric imager and the COR-2 coronagraph; SOHO's LASCO C3, a stalwart of solar observation for nearly 3 decades; and GOES 19's CCR-1, the newest addition to space-based coronagraph arrays, launched just last year for operational space weather monitoring. 4 distinct instruments, from 4 different vantage points, provided 4 sets of data, all indicating the same phenomenon. 3I Atlas brightened considerably as it approached perihelion, and its emitted light shifted towards the blue end of the spectrum. The color measurements are precise. LASCO utilizes multiple filters, including blue, orange, deep red, and infrared, in addition to its standard clear filter. When the blue filter images of 3 Atlas were superimposed, the comet appeared zero point 0.7 magnitudes brighter than in the clear filter image. This represents an increase in brightness of nearly double. In the orange filter, the comet was still zero point 0.4 magnitudes brighter than in the clear filter, indicating that it was emitting more light at shorter wavelengths, the opposite of what dust typically does to sunlight. CCR1 independently corroborated these findings. Its spectral range spans from 470 to 740 nanometers, shifted approximately 40 nanometers bluer than LASCO's clear filter. This minor difference in wavelength sensitivity provided CCR1 with an advantage in detecting the blue emission. The comet registered zero point 0.4 magnitudes brighter in CCR1 than in LASCO's clear filter. Different spacecraft, different orbits, yet the same outcome. Here's why this is significant. Dust particles scatter light. This is a fundamental property. When sunlight strikes a dust particle, shorter blue wavelengths are scattered more efficiently than longer red wavelengths. This phenomenon, known as Rayleigh scattering, is responsible for the blue color of Earth's sky and the red hues of sunsets. Dust particles tend to make objects appear redder, not bluer. Every comet ever observed, from the most prominent naked-eye visitors to the faintest telescopic targets, has exhibited this reddening effect. The dusty coma reflects sunlight, but it shifts this reflected light towards longer wavelengths. 3 Atlas did the opposite. It outshone the sun in blueness. This type of spectral shift can only be produced by emission, not reflection. Hot gases emit light at specific wavelengths, corresponding to the energy transitions of their constituent atoms and molecules. Ionization excites atoms, and as they return to their ground state, they release photons. For instance, CN emits in the violet spectrum, C2 is responsible for the characteristic green glow of the swan bands, and NH2 contributes to the blue and near-ultraviolet emissions. However, attributing the blue color to gas emission presents a challenge. The instruments that detected this phenomenon were not primarily designed for gas analysis. Stereos HI1 and COR2 possess spectral ranges that largely miss the C2 swan bands. HI1 operates approximately from 595 to 720 nanometers, with some overlap into the blue and infrared. COR2 covers 670 to 750 nanometers. Both are shifted too far towards the red spectrum to efficiently capture C2 emissions. Yet, both instruments indicated a brighter than expected comet. LASCO's blue filter, however, does efficiently capture C2 emissions, as does CCR1's broader spectral range. The fact that these instruments observed a brighter comet in blue is consistent with the presence of gas emission. But for HI1 and QR2 to have been so sensitive to it suggests either that the gas emission was so intense that even the red edge of the spectral lines dominated over dust scattering, or that another source was producing the blue light. Yang and Batams meticulously analyzed the brightness evolution. They corrected for the distance to Earth, accounted for the phase angle, and fitted the heliocentric dependence. The result is startling. 3 Atlas brightened as it approached the sun with a power law exponent of negative 7.5 plus or minus 1. In simpler terms, as the comet drew nearer to the sun, its brightness increased at a rate described by 1 over the distance to the power of 7.5. Most Oort cloud comets, those distant visitors from the far reaches of our solar system, brighten with a power law exponent between 2 and 4. An exponent of 2 would imply that brightness scales directly with the amount of sunlight hitting the surface, indicating no significant activity beyond simple reflection. An exponent of 3 or 4 suggests moderate sublimation, where gas production increases as temperature rises. However, an exponent of 7.5 signifies an explosive, runaway sublimation process, or something so convincingly mimicking it that distinguishing between the two is impossible. The paper's conclusion is carefully phrased. The reason for 3 Atlas's rapid brightening remains unclear. The authors acknowledge that the observed rate significantly exceeds what is typical for Oort cloud comets at similar distances. They highlight the blue color, the gas emission, and the unusual spectral properties. They tentatively suggest that perhaps carbon dioxide sublimation suppressed water ice sublimation at greater distances, and now, closer to perihelion, water ice has become dominant, leading to violent expulsion. However, they refrain from a definitive pronouncement because the data does not perfectly align. The brightness curve is too steep, the blue shift too pronounced. The entire phenomenon appears to be operating at an intensity level that should not be possible for an object of this size at this distance. Let's delve into the implications of the blue color. Based on initial spectroscopic analysis, the surface of 3I Atlas is inherently red. Tholins, complex organic molecules formed by the interaction of radiation with simple ices, coat the nucleus. Tholins are dark, reddish-brown, resembling ancient ice exposed to cosmic rays for billions of years. They efficiently capture wavelengths of blue light, which should make the comet appear even more crimson than simple ice would. The observation of blue light implies its generation within the coma itself, not merely reflection from the surface. Gas molecules, when excited by solar ultraviolet radiation, emit light at their specific characteristic frequencies. This is a standard phenomenon. Every active comet exhibits a gaseous coma, but its intensity is crucial. The balance between gas emission and dust scattering dictates the comet's overall hue. For Comet 3I 2019 Y4 Atlas to present a bluer appearance than the Sun, the gas emission must be overwhelmingly dominant, completely obscuring the dust's contribution. Jacques Crozier and his team at the Paris Observatory, utilizing radio telescopes, detected oxygen emission from Comet 3I 2019 Y4 Atlas. The hydroxyl radical, OH, is a byproduct of water. When water molecules are released from the nucleus and subjected to solar ultraviolet rays, they dissociate into hydrogen and OH. This OH then fluoresces at radio wavelengths. Crozier measured the OH production rate between October 13th and October 19th, immediately preceding its closest approach to the Sun. The rate was measured at 5.7 multiplied by 10 to the power of 28 molecules per second, with an uncertainty of approximately 10%. For comparison, the last pre-perihelion optical measurement of OH, taken on September 12th, when the comet was 2.19 astronomical units from the Sun, indicated a production rate of 10 to the power of 27.15 molecules per second. The current measurement is 10 to the power of 28.76, which is roughly 40 times higher. In the span of 1 month, the OH production rate escalated by a factor of 40. The power law connecting these two measurements has an exponent of 8.3, indicating an even steeper increase than the observed optical brightness. If this OH production rate accurately reflects water sublimation, then water production is accelerating faster than dust production, which would account for the blue shift and explain why instruments like LASCO and CORE-2 observe the comet as significantly brighter than anticipated. However, this also brings us back to the issue of mass loss. If water is sublimating at the rate suggested by the OH measurements, then Comet 3I 2019 Y4 Atlas is shedding billions of tons of material. The resultant plume should be immense, with the coma expanding and glowing, filling the field of view with scattered light and fluorescent emissions. CORE-2 did resolve the comet as an extended source. Its stacked images depict a fuzzy sphere approximately 4 arc-minutes in diameter, contrasting with a nearby star that appears as a point. 4 arc-minutes at a distance of 235 million kilometers corresponds to a physical dimension of about 270,000 kilometers. The coma is indeed substantial and physically extended, but is it sufficiently large? Is it sufficiently luminous? Is it consistent with a loss of approximately 1/16th of the nucleus's mass within a month? We will not know the definitive answer until the JUICE mission arrives. We will not have a clear understanding until ground-based telescopes can observe Comet 3I 2019 Y4 Atlas against a dark sky, rather than in close proximity to the Sun. Our knowledge will remain incomplete until instruments like the Hubble Space Telescope and the James Webb Space Telescope direct their mirrors towards this object and capture deep exposures using all their available spectrographs. What is unequivocally clear is that Comet 3I 2019 Y4 Atlas's interaction with solar radiation is extreme. The surge in brightness is extreme. The spectral shift is extreme. The timing of its peak activity, coinciding precisely with perihelion, is characteristic of spacecraft performing orbital maneuvers, not typical cometary behavior. Comets are inherently unpredictable. They do not activate or deactivate instantaneously like light switches, nor do they synchronize their activity levels perfectly with orbital mechanics. Yet, this is precisely what we are observing. An additional detail within the publication by Jian and Batam warrants attention. They highlight that the phase angle during the majority of these observations was notably low, ranging between 1.7 and 10.4 degrees. The phase angle represents the angle formed between the Sun, the comet, and the observer. A low phase angle signifies that we are viewing the comet with the Sun positioned almost directly behind us, analogous to observing a full moon rather than a crescent. At such low phase angles, cometary tails can orient themselves in nearly any direction relative to our line of sight. This is particularly true for ion tails, which follow the trajectory of the solar wind, unlike dust tails that predominantly point directly away from the Sun. The Core 2 imagery does not reveal a distinct tail, only the extended coma. However, the image stacking process encompassed a 6-day period during which the direction towards the Sun shifted by 125 degrees, as observed from geostationary operational environmental satellite GOES-19. Any structure aligned with the Sun would consequently become smeared out. An ion tail tracking the solar wind would blur into the general appearance of the coma. The researchers explicitly note this effect. The absence of a visible tail does not equate to the absence of a tail altogether. It merely indicates that the observational geometry and the stacking methodology rendered it undetectable. Nevertheless, there is something disquieting about an object exhibiting such pronounced activity while displaying a remarkably compact structure. Typically, comets develop extensive tails as they approach the Sun. Historically, the most spectacular comets, such as Hale-Bopp, Hyakutake, and McNaught, all manifested tails stretching across vast swathes of the sky. Comet 3I 2019 Y4 Atlas is at its perihelion, the point of maximum activity, and we are observing a coma but no dramatic tail formation. Perhaps it is a matter of geometry. Perhaps it is a function of the dust-to-gas ratio. It is conceivable that Comet 3I 2019 Y4 Atlas is unusually deficient in dust, primarily emitting gas, and gas tails are less discernible from certain perspectives. This is a possibility. However, these possibilities are beginning to accumulate. We have maybe this, maybe that, and maybe the other thing. At what juncture do we cease relying on speculation and commence questioning the validity of our fundamental assumptions? The blue coloration is an established fact. The brightness curve is an established fact. The timing of peak activity is an established fact. The presence of an extended coma is an established fact. Collectively, these observations paint a picture of an object undergoing intense activity at its perihelion, precisely when and where a comet is expected to be most dynamic. Everything appears to align. It all makes logical sense, except for the aspect of having to expel 5 billion tons of mass within the next few weeks. And we are on the cusp of discovering whether this indeed occurs. Jian and Batum conclude their paper with a deliberately open-ended statement. They assert that the post-perihelion behavior of Comet 3I 2019 Y4 Atlas remains uncertain, with a plateau in brightness being as plausible as a rapid decline. They advocate for continuous observation to provide a more conclusive explanation for the comet's observed behavior. In essence, their message translates to, "We have no clear understanding of what will transpire next. The data is anomalous, the underlying physics are not fully understood, and immediate deployment of additional telescopes is imperative." The month of November will be decisive. Either the blue light will diminish as Comet 3I 2019 Y4 Atlas recedes from the Sun and its sublimation rate decreases, or it will not. The coma will either expand into a vast conspicuous plume of gas and dust, or it will not. The brightness will either follow a predictable decay curve, or it will not. And if it does not, if Comet 3I 2019 Y4 Atlas emerges from behind the Sun still compact, still luminous, still accelerating without apparent mass loss, then the blue light will transition from being a curious spectroscopic anomaly to serving as evidence of something else entirely. It would suggest the presence of something that generates light through mechanisms other than sublimation, something that glows blue due to extreme heat, ionization, or energy absorption from processes not observed in naturally occurring comets. The coronagraphs performed their function admirably, capturing the critical moment. Now we must await the interpretation of that captured instant. On October 29th, coinciding with Comet 3I 2019 Y4 Atlas's passage behind the Sun near its perihelion, a different kind of disturbance erupted across social media. Brian Cox, a physicist and highly influential science communicator with millions of followers, declared he had had enough of speculative theories. He issued a post that ignited one of the most public and acrimonious disputes in contemporary astronomy. To be absolutely clear, Cox stated, given the recent online discourse, Comet 3I 2019 Y4 Atlas is a comet composed of carbon dioxide and water ices, along with other constituents. Its origin is entirely natural. Its orbital path is as anticipated, and it will traverse the Sun before continuing its journey into the galaxy. The word he chose was drill, not speculation or hypothesis. He followed this statement the subsequent day with another pointed remark. I continue to encounter AI-generated content featuring me on YouTube. The general guideline is that if you encounter something I purportedly say that aligns with your beliefs, and you identify as a UFO enthusiast, a flat earther, or believe Comet 3I 2019 Y4 Atlas is a spacecraft, then that content is fabricated. UFO person, flat earther, spaceship believer. 3 distinct categories, grouped together with the same level of credibility. According to Brian Cox, anyone suggesting Comet 3I 2019 Y4 Atlas might be something other than a natural comet is being lumped in with individuals who believe the Earth is flat and that vaccines contain microchips. Avi Loeb responded on the same day. He did not post on social media. That is not his modus operandi. Instead, he published an entry on Medium, a platform he has utilized for dozens of posts since July, calmly presenting data and posing challenging questions, while the broader astronomical community seemingly ignored him. He wrote, "A few reporters approached me today regarding the strong pronouncements made by science popularizer Brian Cox, who asserted with conviction that Comet 3I 2019 Y4 Atlas is unequivocally a natural comet. I explained that Brian Cox has not authored a single scientific paper concerning Comet 3I 2019 Y4 Atlas. He operates as a science popularizer rather than a researcher actively engaged with the relevant scientific investigations pertaining to 3I 2019 Y4 Atlas. In contrast, I have authored 11 scientific papers in recent months focused on 3I 2019 Y4 Atlas. 11 papers versus 0. This is not a rhetorical exaggeration. It is a citation count. Loeb meticulously listed and linked these papers, providing their astrophysics data system identifiers for independent verification. These were 11 peer-reviewed publications, some authored solely by him, others with collaborators, all concentrating on Comet 3I 2019 Y4 Atlas. Its orbital dynamics, spectroscopy, mass estimations, kinematic origins, correlation with the WOW signal, and non-gravitational acceleration. Each paper was supported by empirical data, and every claim was grounded in measurements. Brian Cox's publication record concerning Comet 3I 2019 Y4 Atlas is conspicuously absent. Not a single paper, not a single conference abstract, not a single technical note filed with the Minor Planet Center or the International Astronomical Union. Loeb did not stop there. Rather than resorting to sweeping generalizations, he proposed that Brian should be challenged to provide explanations for the 9 anomalies associated with Comet 3I 2019 Y4 Atlas. Scientific truth, he argued, is not determined by popularity contests, but by meticulous attention to data, particularly when that data is anomalous. 9 distinct observations that do not readily conform to the natural comet hypothesis as smoothly as Cox's dismissive tweets imply, and Loeb has documented each of them, calculated their statistical probabilities, and published the methodologies and findings in the scientific literature. Cox possesses a PhD in particle physics and conducted research at CERN on the ATLAS experiment, investigating proton-proton collisions at energies sufficient to generate exotic particles. He holds a professorship at the University of Manchester and has hosted BBC television programs, authored best-selling books, and toured extensively as a public speaker. He is undoubtedly brilliant, charismatic, and revered by millions who perceive him as the approachable face of science, akin to a 21st-century Carl Sagan. However, he is not a specialist in comets, nor is he an expert in orbital dynamics or an observational astronomer who dedicates nights to collecting spectra and photometric data. His expertise lies in high-energy physics and the behavior of subatomic particles under extreme conditions. While this knowledge is invaluable and his work is important, it is not directly pertinent to the question of whether an interstellar object follows a natural trajectory or exhibits signs of technological origin. Loeb, too, is not a traditional cometary expert. He is a theoretical astrophysicist, formerly the chair of Harvard's astronomy department and the director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. He has published over 1,000 papers covering topics ranging from black holes and the first stars to the habitability of exoplanets. He possesses a profound understanding of data analysis, orbital mechanics calculations, and the assessment of statistical significance in anomalies. Furthermore, he has led the Galileo project since 2020, a multi-million-dollar initiative specifically established to employ rigorous scientific methods in the search for evidence of extraterrestrial technology. This is not a fringe operation. It is funded by private donors, staffed by credentialed scientists, and equipped with custom-built observatories located at Harvard, Colorado, and California. Their objective is not to pursue UFOs with shaky phone cameras, but to gather calibrated multi-wavelength data on aerial phenomena and celestial objects exhibiting unusual characteristics. Comet 3I 2019 Y4 Atlas squarely fits this description: unusual characteristics, anomalous properties, and data that deviates from standard expectations. When Loeb points this out, when he publishes papers calculating the probability that Comet 3I 2019 Y4 Atlas's trajectory alignment with the ecliptic plane is coincidental, or that its sunward jet is an optical illusion, or that its nickel-to-iron ratio is consistent with a natural comet, he is not fabricating information. He is meticulously performing calculations, demonstrating his methodology, and inviting critique from fellow scientists who can verify his computations or identify any errors. Brian Cox neither examined these calculations nor engaged with the data. He simply dismissed it as "dryle" and proceeded. His millions of followers, reassured by his pronouncements, accepted that the alarming alien hypothesis was merely internet fodder generated by attention-seeking contrarians. However, the situation becomes more intricate with the involvement of Chris Lintott. Lintott, an astronomer at Oxford, commands considerable respect within his field, primarily recognized for co-founding Galaxy Zoo and other citizen science projects that enable public participation in genuine astronomical research. He serves as the editor of research notes of the American Astronomical Society, a journal that disseminates concise updates and preliminary findings. Back in July, Loeb submitted a paper to this journal, a straightforward analysis of Comet 3I 2019 Y4 Atlas's trajectory and its alignment with the ecliptic plane, including a statistical assessment of the likelihood of such an alignment occurring by chance. The paper briefly mentioned that if the object were of technological origin, such an alignment could be intentional, representing a navigational choice to facilitate planetary encounters. Lintott, in his editorial capacity, contacted Loeb. He requested that Loeb remove any reference to the possibility of technological origin. He asked him to delete that specific section, allowing discussion of the statistics and trajectory, but explicitly forbidding any mention of aliens, spacecraft, or the hypothesis of an artificial object. Loeb declined this request, not due to a commitment to the alien hypothesis itself, but because of his unwavering dedication to scientific openness. The paper was not asserting that Comet 3I 2019 Y4 Atlas was definitively artificial. Rather, it posited that if such an object existed, its trajectory might resemble the described pattern. This was a conditional statement, a theoretical exploration, the kind of intellectual exercise scientists are expected to undertake when confronted with data that diverges from established models. Lintott remained firm. Remove the section, or the paper would not be published. Loeb acquiesced and removed the offending passage. The paper was subsequently published, after which Loeb, collaborating with different co-authors, submitted another paper titled "Is the Interstellar Object 3I 2019 Y4 Atlas Alien Technology?" This title explicitly stated the hypothesis, which he submitted to a different journal where editors would not censor such inquiries. That paper includes a disclaimer. We strongly emphasize that this is largely a pedagogical exercise with interesting discoveries and strange serendipities worthy of a record in the scientific literature. By far, the most likely outcome will be that 3I 2019 Y4 Atlas is a completely natural interstellar object, probably a comet, and the authors await the astronomical data to support this likely origin. The authors acknowledge the high probability of a natural origin and the need for supporting data, yet they deem it worthwhile to explore the technological hypothesis to calculate its predicted outcomes and then compare these predictions with observational data to ascertain which model offers a superior fit. This is the fundamental process of science, proposing a hypothesis, deriving predictions, gathering data, and comparing the two. The hypothesis that withstands scrutiny, that makes the most accurate predictions with the fewest ad hoc adjustments to align with observations, is the one tentatively accepted until superior data or theoretical frameworks emerge. However, this iterative process is not currently unfolding with Comet 3I 2019 Y4 Atlas. Instead, we observe two distinct factions. One faction unequivocally declares it to be a comet, labeling any suggestion to the contrary as pseudoscientific and asserting that alternative explanations need not be seriously considered because the answer is already known. The other faction advocates for an open-minded approach, remaining receptive to all possibilities, accumulating the maximum possible data, and allowing observations to dictate reality rather than preemptively deciding based on comfortable beliefs. The first faction holds a significant numerical advantage. The majority of astronomers concur that Comet 3I 2019 Y4 Atlas is almost certainly a comet. Most press releases identify it as such, and public communication generally treats the matter as definitively resolved. In the vast majority of instances, this approach is appropriate. Most interstellar objects are indeed natural, and most comets are simply comets. The leap to extraordinary conclusions without extraordinary evidence is a hallmark of flawed scientific practice. However, the second faction raises valid points. The evidence supporting Comet 3I 2019 Y4, Atlas's classification as a conventional comet, is less robust than the confident pronouncements suggest. The anomalies are genuine, and the statistical probabilities are concerning. The fact that every explanation necessitates the invocation of special circumstances, unusual compositions, or rare geometrical configurations begins to resemble a hypothesis being shielded by epicycles rather than substantiated by empirical data. Cox's dismissive statement was particularly stinging because it completely circumvented the substantive scientific arguments. He failed to address the 9 anomalies, did not explain why the trajectory alignment is insignificant, nor why the nickel abundance is entirely natural, or why the solar jet is merely an optical illusion. He simply declared it drill, and his considerable authority as a public scientist was sufficient to persuade millions that Loeb was mistaken. Loeb's response was measured yet pointed. He refrained from personal attacks on Cox, nor did he question his intelligence or his credentials in particle physics. He simply highlighted that Cox had not conducted the necessary research on this specific problem, effectively commenting from the sidelines as a spectator rather than an active participant. In the scientific realm, the opinions of those who perform the work, gather the data, and publish the findings are the ones that carry genuine weight. Lintot's role, while more subtle, has potentially more damaging implications. As an editor, he wields the power to influence what gets published and what does not. By pressuring Loeb to omit the technological hypothesis from a paper that was otherwise scientifically sound, he was not safeguarding the integrity of science. Instead, he was protecting the comfort of scientists who prefer to avoid confronting uncomfortable questions. This phenomenon occurs more frequently than the public is typically aware. Scientific journals possess inherent biases, editors have personal preferences, and peer reviewers hold opinions regarding what constitutes legitimate research versus fringe speculation. These biases, preferences, and opinions collectively shape the publication landscape, determining which ideas gain traction and which are rejected. This selection process is not always dictated by the quality of the data or the rigor of the analysis, but rather by whether the conclusions align with the prevailing sentiments of the scientific community. Loeb has been contending with this filtering mechanism for years, notably with Oumuamua, his research into alien technology, and the Galileo project. He is willing to pose questions that make his colleagues uncomfortable and to endure ridicule and professional backlash because he believes these questions are fundamentally important. He contends that, as a species, we owe it to ourselves to examine the universe without preconceived notions, to follow the data wherever it may lead, even if that destination is unexpected. Cox and Lintot represent the opposing perspective, the view that emphasizes caution, conservatism, and skepticism towards extraordinary claims. This side prioritizes public perception, the maintenance of credibility, and the avoidance of providing ammunition to conspiracy theorists and proponents of pseudoscience. They perceive Loeb's openness to the technological hypothesis as reckless, dangerous, and irresponsible. Both viewpoints possess merit. Both factions hold science in high regard, both aiming for accurate conclusions, yet they fundamentally diverge on the methodology. This public discord, amplified across social media, blogs, and interviews, exposes a schism within the scientific community that extends beyond superficial disagreements. It delves into the very essence of scientific inquiry. Who is permitted to pose questions, what theoretical frameworks are deemed acceptable, and whether we are genuinely open to novel discoveries or rigidly committed to predetermined possibilities, dismissing anything outside those confines as inherently flawed. The poignant truth is that empirical evidence, not the opinions of individuals like Cox, Loeb, or Lintott, will ultimately resolve this. The data collected when the JUICE spacecraft observes 3 Atlas on November 4th, when ground-based observatories get their chance in mid-November, and when the Hubble and Webb telescopes capture their deep-field images in December, will either substantiate the natural comet hypothesis or invalidate it. The presence or absence of a discernible plume, the correlation of observed acceleration with mass loss, these will be the deciding factors. Once this evidence is available, one side will be vindicated, and the other will be compelled to account for their certainty in an incorrect outcome. This is the essence of scientific progression, formulating predictions, subjecting them to rigorous testing, and accepting the results, even when they deviate from our expectations. Nevertheless, the intellectual battle continues. Cox decries the situation as nonsensical, Loeb highlights the dearth of peer-reviewed research, and Lintott attempts to expunge inconvenient hypotheses. Meanwhile, millions observe, striving to discern who merits trust, who to believe, who is engaged in genuine scientific pursuit, and who is merely seeking notoriety. Frustratingly, the reality is that all are conducting actual science, albeit with differing priorities and varying thresholds for uncertainty. Cox seeks to shield the public from unwarranted optimism and unsubstantiated theories. Lintott endeavors to uphold academic integrity and prevent scholarly journals from devolving into conduits for unverified concepts. Loeb's concern is that we might overlook significant discoveries due to an unwillingness to explore unconventional avenues. November 4th marks the commencement of the arrival of new data, just 4 days away. Following this, the discourse will pivot from interpersonal dynamics to factual evidence, shifting the focus from the authority to ask questions to the actual answers that emerge. One way or another, 3 Atlas is poised to settle this debate, not by definitively declaring any party right or wrong, but by furnishing evidence that is sufficiently clear, robust, and unambiguous for both sides to acknowledge its validity. Until that moment, the internal conflict within the scientific community persists, playing out across tweets, blog posts, research papers, and press releases, all while a celestial object, approximately 5 kilometers in diameter, traverses the void, utterly indifferent to the human drama unfolding in its wake. The point of closest approach to the sun, its perfect concealment. October 29th at 11:47, Universal Time, perihelion. This was the precise moment when 3 Atlas achieved its nearest proximity to the Sun, a distance of 203 million kilometers, positioning itself precisely between the orbital paths of Mars and Earth. For a celestial body exhibiting cometary characteristics, this celestial alignment is merely a matter of orbital mechanics. However, for a constructed vehicle, this moment represents a crucial opportunity. The Oberth effect stands as one of the most elegant principles in astronautics. Within a substantial gravitational field, where an object achieves its peak orbital velocity, any application of propulsive force is significantly amplified. The existing kinetic energy effectively magnifies the efficacy of the engine's operation. While initially counterintuitive, one might assume the timing of rocket ignition is inconsequential, believing a fixed quantity of fuel yields a consistent change in velocity. This, however, overlooks the complexities of orbital mechanics. The energy gain from an engine burn is contingent not only on the thrust itself, but also on the velocity at the moment of application. Envision yourself riding a bicycle down a steep incline. You are already moving at a considerable speed. Now you begin to pedal. Each exertion adds to your existing momentum. Because you are already traveling swiftly, this addition results in a substantially greater increase in kinetic energy than if you had exerted the same effort while moving at a slower pace. This principle, scaled to the magnitude of spacecraft traversing gravitational wells, is precisely what is at play. For 3 Atlas, perihelion represents the nadir of the gravitational influence, the point at which solar gravity has propelled it to its maximum velocity. It is at this juncture that any additional thrust, any course correction, any alteration in velocity yields the most pronounced effect on its ultimate trajectory. If navigational adjustments are to be made, if its path through the solar system is to be modified, this is the opportune moment. Not before, not after, but precisely at this instance. And it was precisely then that the non-gravitational acceleration was detected. Pure coincidence? Perhaps. Comets typically exhibit heightened activity around perihelion due to maximal solar flux and temperature, leading to peak sublimation rates. If 3 Atlas is indeed a comet, it stands to reason that its most vigorous outgassing phenomena would occur near its closest solar approach. All predictive models and observations of other comets corroborate this expectation. However, a disquieting detail emerges. The timing is remarkably precise, not merely proximate to perihelion, but precisely at perihelion. Neither several days prior nor several days subsequent, but at the exact moment when a propulsive maneuver would be most effective. The statistical probability of natural outgassing intensifying to produce a measurable acceleration at the exact optimal moment for a gravitational assist is exceedingly low. It is not an impossibility. Nature does not adhere to human engineering timelines. Nevertheless, the probability is low enough to warrant contemplation, low enough to provoke inquiry. Further compounding this, another observation renders the situation less likely to be coincidental and more suggestive of deliberate planning. 3 Atlas achieved perihelion while Earth occupied the diametrically opposite side of the Sun, a solar conjunction. From our vantage point, the comet and the Sun appeared in close proximity in the sky, separated by less than 3 degrees. Ground-based telescopes are incapable of observing objects situated so near the Sun, as the overwhelming glare of daylight obscures all detail. Even observations shortly after sunset or before dawn become unfeasible when a target is within approximately 15 degrees of the Sun. From October 21st through November 14th, 3 Atlas remained effectively imperceptible from Earth. This period of 24 days, nearly a month, coincided with its peak activity, its most engaging physical processes, and the very time when any anomalous behavior would be most readily detectable. Was this trajectory deliberately orchestrated? Was a calculation made to identify the most advantageous path through the inner solar system, one that would facilitate a close solar encounter for a gravitational assist while simultaneously positioning it behind the Sun from Earth's perspective during a critical maneuvering window? The computations involved are not trivial, but they are certainly achievable. With knowledge of Earth's future position, the Sun's location, and control over its own trajectory, such a precise alignment is possible. It is conceivable to engineer a perihelion passage on the far side of the Sun relative to Earth's orbital position. This is a common practice for mission planners of solar observation spacecraft that require avoidance of Earth's radio interference during crucial data collection periods. While 3 Tau A Atlas had no need to evade Earth's radio transmissions, the strategic use of solar conjunction would serve perfectly to elude Earth-based optical telescopes during a vital propulsive maneuver. What we do know with certainty is what transpired during its perihelion passage. The space-based coronagraph instruments detected its presence. Stereo A was positioned approximately 47 degrees ahead of Earth in its orbit, meaning that from Stereo's perspective, 3EI Atlas was not concealed behind the Sun, but rather observable to the side, within the fields of view of both the COR-2 coronagraph and, earlier in September, the HI-1 heliospheric imager. SOHO, positioned at Earth's Sun L1 Lagrange point, perpetually situated between Earth and the Sun, captured 3 Atlas with its LASCO C3 instrument in mid to late October as the object traversed its field of view. GOES 19, in geostationary orbit around Earth, provided a similar yet distinct vantage point, with its CCR-1 camera recording the object between October 18th and 24th. 4 instruments deployed from 4 different locations, all designed for solar study, not cometary observation, yet all possessing the capability to detect bright objects passing through their fields of vision. And all of them documented 3 Atlas during its perihelion passage, a passage purportedly shrouded from observation. Consequently, we do possess observational data. While not high-resolution imagery or detailed spectroscopic analysis, nor the kind of observations obtainable from a dedicated telescope meticulously tracking the comet with optimized filters and exposure times, the data is sufficient to ascertain its luminosity, measure its photometric properties, detect the presence of an extended coma, and confirm its physical existence and observable activity. What the coronagraphs did not, and indeed could not, resolve were fine details. They failed to delineate the nucleus or image any distinct structures, such as fragments detaching or jets emanating from specific surface regions. The spatial resolution simply does not permit such granular observation. The CCR1, with its 19 arcsecond pixels, can barely distinguish between an extended object and a point source. The LASCO C3 is even coarser, with 56 arcsecond pixels. These instruments are engineered to image the solar corona, vast structures spanning millions of kilometers. A 5-kilometer nucleus, in comparison, is infinitesimally small. Therefore, we have confirmation that 3II Atlas increased in brightness, developed an encompassing coma, and exhibited a shift in color towards blue. However, we lack definitive knowledge regarding potential fragmentation, alterations in its rotational period, or the appearance of discrete features that might suggest localized venting rather than uniform surface sublimation. This lack of detail is problematic, as these very specifics are crucial. A natural comet experiencing thermal stress at perihelion is prone to fracturing. The ice binding the nucleus together weakens as temperatures rise, and thermal expansion induces stress. Rapid outgassing can dislodge significant portions of the surface. This is not an uncommon phenomenon. Comet Shoemaker-Levy 9 famously fragmented into over 20 pieces before impacting Jupiter, and Comet Schwarzmann-Wachmann 3 fractured into numerous pieces during a close solar passage. Fragmentation is an anticipated consequence when comets approach the Sun too closely, and their structural integrity is compromised by the intense heat. If 3 Atlas fragmented, the coronagraphs may not have been able to discern it. The fragments, in their initial proximity, would have remained within the same celestial patch and appeared as an unresolved entity. Only over days or weeks, as these fragments diverged along slightly different trajectories, would they become individually discernible. Conversely, if 3 Atlas remained intact, enduring 770 watts per square meter of solar irradiation while expelling billions of tons of mass through sublimation, then it either possesses an exceptionally robust structure for a cometary nucleus, or is not losing as much mass as its acceleration suggests. Both scenarios present challenges for the natural explanation. Cometary nuclei are not typically characterized by remarkable structural integrity. They are often described as rubble piles, loosely aggregated collections of ice and rock, held together by weak gravitational forces and the cohesive properties of frozen volatiles. Exposure to heat and subsequent ice evaporation can lead to disintegration. The possibility that 3EI Atlas might have survived perihelion intact, assuming it did, suggests either an unusually resilient internal structure or a composition dissimilar to that of typical comets. Alternatively, it implies that the object's integrity is not derived from ice and gravity alone, but from an external source, something artificial, engineered to withstand thermal stress and mechanical forces without fracturing. The truth will soon be revealed. As 3I Atlas emerges from behind the Sun in mid-November, ground-based telescopes will obtain their first clear observations of its post-perihelion state. If fragmentation occurred, multiple objects will be visible where only one existed previously. If it remained intact, a single nucleus will be observed, potentially larger or smaller than before, depending on the extent of mass loss, but still cohesive and continuing along its orbital path. JUICE will provide the initial observations on November 4th. The European Space Agency's Jupiter Icy Moons Explorer, currently en route to the outer solar system, carries a sophisticated array of cameras and spectrometers designed to study Europa, Ganymede, and Callisto, the large icy moons suspected of harboring subsurface oceans capable of supporting life. While JUICE was not designed for cometary research, it is equipped with cameras, and 3 Atlas will pass within 64 million kilometers of the spacecraft's current position. 64 million kilometers may seem a vast distance, but in astronomical terms it is relatively close. This proximity is sufficient for JUICE's instruments to resolve the coma, measure its brightness, and potentially collect spectral data if the comet is sufficiently luminous. The geometrical alignment is highly favorable. The solar elongation from JUICE's perspective exceeds 18 degrees, placing it sufficiently distant from the sun's glare to permit feasible observations. Furthermore, unlike Earth-based observatories, JUICE will not be hampered by twilight conditions or atmospheric turbulence. It is in space, enjoying an unobstructed view at a time when 3I Atlas should still be actively sublimating if the perihelion heating induced significant outgassing. The data from JUICE will serve to constrain the prevailing hypotheses. If the coma remains substantial, if its brightness persists at high levels, and if spectral lines indicate ongoing gas production at rates consistent with the calculated mass loss, then the natural comet hypothesis will receive considerable support. This would imply that the detected acceleration originated from outgassing, as initially theorized, and that the object is behaving in accordance with expectations for a volatile-rich nucleus near perihelion. Conversely, if the coma appears diminished, if its luminosity declines more rapidly than sublimation models predict, indicating an absence of the billions of tons of gas that should be surrounding the nucleus, then a significant problem arises. In such a scenario, the acceleration cannot be explained by outgassing, necessitating an alternative mechanism. The inventory of plausible alternative mechanisms is remarkably limited, disturbingly so. Furthermore, the question of the trajectory's evolution arises. Has it undergone alteration? The 4 arcsecond deviation recorded by ALMA on October 29th confirms the presence of acceleration, but acceleration over a limited duration does not necessarily translate to a substantial trajectory change. The magnitude, duration, and direction of the acceleration are critical factors. Brief, low-magnitude thrusts might subtly adjust the orbit without drastically altering its path. Larger thrusts or sustained burns, however, would result in noticeable deviations. NASA's Jet Propulsion Laboratory, JPL, routinely updates orbital elements as new observational data becomes available. The current ephemeris for 3I Atlas, designated orbit number 27, incorporates the non-gravitational acceleration parameters submitted by Finocchi. These parameters quantify the extent to which the trajectory deviates from purely gravitational influence. As additional data streams in from JUICE, ground-based telescopes, Hubble, and Webb, JPL will refine the orbital calculations, update the non-gravitational terms, and reveal whether the observed acceleration represented a transient spike or a sustained phenomenon. If it was a brief event, lasting only a few hours or days around perihelion, it could be attributed to peak solar heating, a surge of sublimation that was intense but short-lived, producing thrust for a limited period before outgassing returned to lower rates. This would align with natural cometary behavior, albeit at an extreme level. If, however, the acceleration was sustained, continuing for weeks both before and after perihelion, then we must consider a more controlled, more deliberate process, less akin to a comet passively responding to thermal input and more indicative of a craft actively modifying its course. The empirical data will provide the answer. JPL's orbital fits will offer crucial insights. The close approach to Earth on December 19th will furnish highly precise astrometric measurements, which can then be compared to pre-perihelion observations. Any discrepancy from the predicted trajectory will be readily apparent. Trajectory modifications cannot be concealed. Orbital mechanics is an exacting science. If 3I Atlas executed a maneuver, we will know. For the present, however, we remain in an observational vacuum. This 24-day interval, during which the most significant object in the solar system is obscured behind the sun, engaging in whatever activities it may be undertaking, is invisible to the telescopes capable of discerning fact from speculation. 4 days remain until JUICE's observations. 14 days until ground-based telescopes can reacquire visual contact. 49 days until its closest approach to Earth, a period during which every major observatory will be focused on 3EI Atlas, diligently collecting data, measuring positions, and comparing observations against predictions. 49 days to ascertain whether perihelion was merely a routine transit through the inner solar system or the juncture at which an extraterrestrial entity executed a meticulously planned gravitational assist, leveraging our sun's mass to alter its trajectory in ways we are only beginning to comprehend. Its perfect concealment, whether by serendipity or by design. And soon, very soon, the answer will be revealed. The elusive mass cloud, 5.5 billion tons of gas. This is not a metaphorical statement, it is a quantitative assessment. It represents the minimum quantity of material that 3I Atlas must have expelled during its perihelion passage if the observed non-gravitational acceleration is attributable to outgassing. This translates to 5,500 million tons. In scientific notation, this is 5.5 multiplied by 10 to the power of 15 grams, or 5.5 petagrams. This mass is equivalent to approximately 50 billion average-sized automobiles, or a cube of ice roughly 2 kilometers on each side, vaporized and propelled into space by solar heating, expanding outward from the nucleus at speeds of hundreds of meters per second, forming a gaseous cloud that should be visible from Earth, from Mars, and from any spacecraft equipped with a camera oriented in the correct direction. Yet, we have not observed this phenomenon, and this absence is becoming increasingly problematic. The calculation is straightforward. Avi Loeb meticulously detailed this on October 30th, the day following perihelion, and any individual with a foundational understanding of physics can verify the figures. Conservation of momentum dictates that as gas molecules depart the surface of a cometary nucleus, they carry momentum with them. This momentum must originate from somewhere. It is derived from the nucleus itself, which recoils in the opposite direction, analogous to a rocket engine expelling exhaust. The product of the nucleus's mass and acceleration is equal to the rate of mass loss multiplied by the velocity of the ejected gas. Rearranging this equation yields the evaporation timescale, the duration required to expel a significant fraction of the nucleus's mass. For 3I Atlas, given the acceleration measured by Finoki, this timescale is approximately 6 months. This means it would take 6 months to lose half its mass. 1 month would suffice to lose 1/16th of its mass. 1/16th of 33 billion tons equates to 5.5 billion tons. This is the estimated quantity of gas that should currently surround 3I Atlas. It is not a possibility, it is a physical necessity. The laws of physics demand it. If the acceleration is real and is caused by outgassing, then the gas must be present. The question then becomes, where is it? The Webb telescope detected a mass loss rate in the spring, prior to perihelion, when 3I Atlas was still several astronomical units from the Sun. The rate was measured at 150 kilograms per second, a steady, continuous outflow over 5 months that amounted to billions of kilograms. However, this mass was dispersed over an extended period and at such a low rate that it did not generate a measurable non-gravitational acceleration. The gas dissipated gradually, forming a tenuous coma detectable by spectroscopy, but not overpowering the reflected sunlight from the nucleus. Now, post-perihelion, the mass loss rate should be exponentially higher. The acceleration data implies a rate thousands of times greater than what Webb observed. At such a rate, the gas should no longer be tenuous. It should be dense, luminous, and conspicuous. Consider the visual implications of 5 billion tons of water vapor in the vacuum of space. Water molecules, H2O, have a molecular weight of 18. Consequently, 5 billion tons equates to approximately 1.7 multiplied by 10 to the power of 32 molecules. This figure represents 100 million trillion water molecules. If these molecules subsequently dissociate into hydroxyl radicals and hydrogen atoms under solar ultraviolet radiation, a process that occurs almost instantaneously, the number of hydroxyl radicals would double to 3, multiplied by 10 to the 32nd O molecules. Each of these would fluoresce at characteristic wavelengths in the ultraviolet and radio spectrum. Radio observations conducted by Jacques Provisier detected O production in mid-October. The rate he measured, 5.7 multiplied by 10 to the power of 28 molecules per second, was already substantial, but this represented a cumulative production over an unspecified averaging period, likely hours or days, depending on the radio telescope's integration time. The total quantity of hydroxyl radicals present in the coma at any given instance is dictated by the production rate and the photodissociation lifespan. This lifespan refers to the duration it takes for solar ultraviolet radiation to disintegrate the hydroxyl radical into oxygen and hydrogen. At a distance of 1 astronomical unit from the Sun, hydroxyl radicals possess a lifespan of approximately 160,000 seconds, roughly equivalent to 2 days. As the object draws closer to the Sun, this lifespan diminishes. At 3 astronomical units, specifically at the perihelion distance of 1.36 astronomical units, the lifespan is somewhat reduced, perhaps to 140,000 seconds. This duration is still substantial enough that if hydroxyl radicals are being generated at a rate of 10 to the power of 28 molecules per second, a stable coma will develop, containing around 10 to the power of 33 molecules at any specific time. This constitutes a considerably large detectable cloud of hydroxyl radicals that fluoresce under solar ultraviolet light, emitting photons, scattering light, and thereby forming a visible halo around the nucleus. Radio telescopes should be capable of observing this phenomenon with ease. Optical telescopes equipped with the appropriate filters should also be able to detect it. Ultraviolet spectrographs are expected to identify absorption or emission lines. This is not a subtle effect. It is not marginal. It represents billions upon billions of molecules broadcasting their existence throughout the electromagnetic spectrum. Nevertheless, as of October 30th, we lack confirmation that it exists on the scale that the observed acceleration would suggest. We possess an observation from Crevier made in mid-October, but this predates perihelion when the object was situated slightly farther from the Sun and presumably less active. We have not yet obtained post-perihelion measurements of hydroxyl radicals. Radio telescopes have not yet published updated observational data. Ground-based optical telescopes are unable to observe 3ITLAs as it is positioned behind the Sun from Earth's perspective. This is where JUICE becomes relevant. JUICE is scheduled to launch on November 4th, a mere 4 days from now. This spacecraft carries several instruments that are capable of detecting the coma, should it exist. JANUS, the optical camera system, can image the comet and quantify its brightness and spatial extent. UVS, the ultraviolet spectrograph, can detect hydroxyl radicals and other species in the ultraviolet spectrum. MAGIS, the visible and infrared spectrometer, can analyze the composition of the coma gas. If 3ITLAs is enveloped by 5 billion tons of sublimated material, JUICE will be able to observe it. The geometrical configuration is favorable. JUICE will be approximately 64 million kilometers away from 3ITLAs, a distance close enough to provide adequate spatial resolution. The solar elongation from JUICE's vantage point exceeds 18 degrees, a sufficient separation to prevent interference from solar glare. The phase angle, which is the angle formed between the Sun, the comet, and JUICE, will be relatively small. This implies that JUICE will be observing the sunlit side of the coma, where activity is expected to be at its peak. If JUICE's cameras reveal a vast, diffuse coma with an apparent size consistent with billions of tons of gas expanding at hundreds of meters per second, then the enigma will be resolved. 3ITLAs would be classified as a comet, albeit an unusual one exhibiting extreme activity, but fundamentally a natural celestial body. The observed acceleration would be attributable to outgassing, and the blue coloration to gas emission. The entire phenomenon would align with established cometary behavior. However, if JUICE's imagery depicts a compact nucleus with only a faint, small coma, inconsistent with the mass loss necessary to account for the measured acceleration, then we face a significant discrepancy. In such a scenario, the calculations would not hold true, implying that something other than natural outgassing is accelerating 3ITLAs without generating the observable signature we would anticipate from sublimation. As Lowe succinctly articulated in his October 30th blog post, if the extensive EON data does not reveal a substantial cloud of gas surrounding 3ITLAs, then cometary evaporation would not serve as a natural explanation for its non-gravitational acceleration. What then remains? What alternative mechanisms can produce thrust without expelling mass, or at least without expelling a detectable quantity of mass? The options are extremely limited. One possibility is radiation pressure acting on an object with low density and a large surface area. However, 3ITLAs is substantial, measuring at least 5 kilometers across and presumably possessing significant density. Radiation pressure is effective on objects such as solar sails, which are thin films with an exceptionally high area-to-mass ratio, not on multi-billion-ton aggregations of rock and ice. Another consideration is solar wind momentum transfer. The solar wind consists of charged particles that could, in principle, exert a push against a conductive surface. However, the effect generated is minuscule, orders of magnitude too small to explain the observed acceleration. To achieve the observed acceleration, one would require a magnetic field, a mechanism to more efficiently couple the solar wind to the object. While this is theoretically possible, it necessitates specific conditions not typically found in natural comets. Alternatively, an engine, an internal propulsion system, a reaction drive that burns fuel or expels reaction mass in a controlled, directed manner could be responsible. This would not necessarily be a rocket in the conventional sense. It could be an ion drive, a plasma thruster, or something more unconventional, but something that generates thrust without producing a massive, visible exhaust plume. This scenario sounds like science fiction. It sounds preposterous. Yet, if the gas cloud is absent, if JUICE returns images of a quiescent, compact object that is nevertheless accelerating, then absurdity begins to appear as the sole remaining possibility. The hypothesis of a dark comet attempts to bridge this divide. A dark comet, by definition, is an object that undergoes outgassing but does not produce a visible coma or tail. This term was devised to explain Oumuamua, which exhibited non-gravitational acceleration without any detectable gas or dust surrounding it. Subsequent observations by Spitzer found nothing. Consequently, comet experts posited that perhaps the gas was present but did not generate a visible signature. They suggested that the dust-to-gas ratio might be exceptionally low or the composition unusually peculiar, causing standard detection methods to miss it. Lowe has highlighted the logical contradiction inherent in this concept. If a comet is defined by the presence of a visible coma and tail, then a dark comet is an oxymoron, akin to speaking of invisible light or silent sound. The coma and tail are the defining characteristics of a comet. Removing these leaves an object that accelerates without an apparent cause, which bears a striking resemblance to a spacecraft rather than a comet. Nevertheless, let us consider the dark comet notion seriously for a moment. Suppose 3. ITLAs is outgassing, but the gas is not forming the luminous coma we expect. How could this occur? It would require the gas to rapidly depart the surface without entraining significant dust, and it would need to be transparent at visible wavelengths. Water vapor fits this description quite adequately. Water vapor itself is invisible and does not scatter light effectively. It only becomes visible when it fluoresces under ultraviolet radiation or when dust particles intermingled with it scatter sunlight. However, hydroxyl radicals, the breakdown product of water, do fluoresce. This is what Crevizier detected using radio observations. An emission from hydroxyl radicals should be discernible in the ultraviolet and at specific optical wavelengths. If 10 to the power of 33 hydroxyl radical molecules are present in the coma, they should be emitting photons at a detectable rate. This emission might not be as bright as that from dust scattering, but it should be measurable with sensitive instruments. JUICE is equipped with such sensitive instruments. UVS is capable of detecting hydroxyl radical emissions. If these emissions are present at the levels predicted by the mass loss calculations, UVS will detect them. Conversely, if UVS fails to detect them and the hydroxyl radical flux is significantly lower than anticipated, it implies one of two things. Either the mass loss is not as substantial as calculated, meaning the acceleration is not originating from outgassing, or the water is not breaking down into hydroxyl radicals, which would be an extraordinary circumstance requiring an explanation rooted in unusual chemistry or shielding from solar ultraviolet radiation. Another possibility exists. Perhaps the mass loss is indeed occurring, but it involves material other than water. Perhaps 3. ITLAs is ejecting substances that do not fluoresce, do not scatter light efficiently, and do not appear in spectral analysis. But what could this material be? Nitrogen, carbon monoxide, noble gases. These substances do not produce strong emission lines in the visible or ultraviolet spectrum. However, they also do not generate substantial thrust. They are light. To achieve the same momentum transfer, they would need to be ejected at exceptionally high velocities, far exceeding the thermal speeds anticipated from sublimation. This brings us back to the concept of an active expulsion mechanism rather than passive evaporation. The elusive mass cloud is the linchpin. If it is present, the natural explanation remains viable. If it is absent, the natural explanation crumbles, leaving us to confront an interstellar object that is exhibiting behavior beyond the capabilities of comets. Ground-based telescopes will have their opportunity to observe starting in mid-November. By that time, 3 ITLAs will have reappeared from behind the sun, and astronomers worldwide will direct their instruments toward it, searching for the coma, measuring its brightness, and collecting spectral data. The International Asteroid Warning Network has already organized a coordinated observation campaign. From November 27th to January 27th, dozens of observatories will track 3 ITLAs, gathering astrometric data to refine its orbit and photometric data to characterize its activity. This constitutes nearly 2 months of intensive observation. If the coma is present, if the gas is emanating at levels commensurate with the acceleration, this campaign will definitively document it. With multiple independent teams, multiple instruments, and observations across multiple wavelengths, there will be no ambiguity, no controversy. The data will be unequivocal. And if the data reveals a faint coma, significantly smaller than predicted, with gas production rates that do not align with the momentum requirements, then every observatory participating in this campaign will have contributed to one of the most significant discoveries in the history of astronomy: the confirmation that an interstellar object is capable of non-gravitational acceleration without the observable mass loss that such acceleration should inherently produce. December 19th is the pivotal date. This marks the closest approach to Earth at a distance of 269 million kilometers. While still considerable by everyday standards, it is close enough for the Hubble Space Telescope to resolve fine details. The James Webb Space Telescope can collect high-resolution spectra. Ground-based telescopes can measure positions with sub-arc-second precision. The observing geometry will be ideal. The observational conditions will be as optimal as they are likely to be for this object. If 3 ITLAs is surrounded by a substantial gas cloud at this juncture, we will be able to observe it. The cloud should be even more extensive than it was at perihelion, as the gas will have had more time to expand. While sublimation may have decreased as the object moved away from the sun, the gas already released will persist, spreading outwards and forming a coma spanning hundreds of thousands, or even millions, of kilometers. Hubble's cameras should capture this with ease. Webb's and NIR-spec instruments can meticulously analyze its composition, identify the molecular species, quantify their abundances, and compare them to solar system comets and theoretical models of interstellar chemistry. However, if Hubble's images show a compact object, if Webb's spectra reveal faint gas lines inconsistent with billions of tons of ejected material, and if the astrometry confirms that the non-gravitational acceleration persisted post-perihelion without corresponding mass loss, then we will possess proof, not mere speculation or hypothesis. We will have definitive evidence that 3 ITLAs is not behaving like a natural comet. The missing mass cloud will either be discovered or it will not. There is no intermediate outcome. The underlying physics is too clear, and the predictions are too specific. 5.5 billion tons is the critical figure, and within the coming weeks, every major telescope in our solar system will be focused on this object, observing it, measuring it, and endeavoring to confirm or refute its existence. 4 days remain until JUICE, the initial test, the first genuine opportunity to ascertain whether the gas is present. And if it is not, if JUICE returns imagery that does not depict the anticipated coma, then we must prepare ourselves for what follows. For an object that accelerates without visible exhaust, is not adhering to the established rules that humanity has painstakingly developed over centuries. It is engaging in something else, something that requires our understanding, something that could represent the most significant discovery in human history or pose the most unsettling question we have ever faced: the missing mass cloud. Either it exists, dispersed across millions of kilometers of space, faintly glowing under solar radiation, awaiting detection, or it does not. And if it does not, then everything changes. The anomaly stack now stands at 9. The non-gravitational acceleration is anomaly number 9. It is not the first oddity, nor even the strangest, but rather the latest in a growing list of characteristics that render 3ITLAs unlike anything we have encountered previously. When these anomalies are compounded, when their probabilities are multiplied, the cumulative odds become astonishing. 1 in 10 quadrillion. This is Lowe's estimation for the combined probability of all 9 anomalies occurring naturally within a single object. 1 in 10 to the power of 16. Written out, this is 1 in 10 million billion. These are not the odds of winning the lottery. These are not even the odds of a cosmic accident. These are numbers so infinitesimally small that they begin to challenge the notion that we are observing a random confluence of natural phenomena. Let us examine them, all 9, one by one. Anomaly 1. Trajectory alignment with the ecliptic plane. 3. ITLA's orbital plane is tilted by a mere 5 degrees relative to the ecliptic, the plane in which Earth and the other planets orbit the Sun. Most interstellar objects are expected to arrive from random directions. The galaxy is a three-dimensional structure with stars distributed throughout its disk and halo. An object ejected from a planetary system light years away should not exhibit a particular alignment with the architecture of our solar system. The probability of arriving within 5 degrees of the ecliptic by chance is approximately 0.2%, or 1 in 500. Anomaly 2. The sunward jet. Between July and August, 3ITLAs displayed an anti-sunward feature, a structure pointing towards the sun rather than away from it. Antigravis can sometimes be optical illusions, perspective effects, where a curved dust tail is viewed from a specific angle. However, a detailed geometric analysis indicated that this was not a matter of perspective. The structure was real and pointed sunward. Comets do not exhibit such behavior. The pressure exerted by solar radiation and the solar wind consistently pushes material away from the sun. A sunward jet necessitates an alternative force, a mechanism that ejects material in a direction opposite to the prevailing flow. The scientific paper documenting this phenomenon concluded that it was inconsistent with known cometary behavior. Anomaly 3. Nucleus mass. 3ITLAs is exceptionally large compared to other interstellar objects, measuring at least 5 kilometers in diameter and potentially larger. Mass estimations place it at 33 billion tons or more. This is approximately 1 million times more massive than Oumuamua and 1,000 times more massive than Borisov. Furthermore, it is moving at a greater velocity than both. Kinetic energy is proportional to mass multiplied by velocity squared. A large, fast-moving object possesses immense energy, and the probability of detecting such an object so soon after we began searching for interstellar visitors is exceedingly low, less than 0.1%, according to population models. Anomaly 4. Water depletion. The gas plume detected by the James Webb Space Telescope and other observatories contained only 4% water by mass. 4%. Most solar system comets are composed of more than 50% water ice, with some exceeding this figure considerably. Water is the predominant volatile in the outer solar system due to its abundance in molecular clouds, the regions where stars and planets originate. A comet with only 4% water is highly unusual, suggesting either a vastly different formation environment or significant processing that has depleted the water content. Anomaly 5. Extreme negative polarization. Polarization quantifies the orientation of light waves after scattering off a surface. Most objects exhibit positive polarization, meaning the reflected light waves tend to align perpendicularly to the plane of scattering. Three ITLAs showed extreme negative polarization, a phenomenon unprecedented for any known comet, including Borisov. The probability of this occurring naturally, based on comparisons with thousands of other measurements, is less than 1%. Negative polarization can occur, but extreme negative polarization is rare and requires specific surface properties that are not characteristic of most comets. Anomaly 6. The WOW signal correlation. In 1977, the Big Ear radio telescope in Ohio detected a strong, narrow-band signal originating from the direction of the constellation Sagittarius. The signal persisted for 72 seconds, its intensity waxing and waning in a manner consistent with the telescope's beam pattern, and it has never been detected again despite numerous follow-up attempts. It was designated the WOW signal, named after the exclamation astronomer Jerry Eman scribbled in the margin of the printout upon its discovery. The origin of the signal remains unknown. It could have been terrestrial interference, an astrophysical transient event, or something else entirely. Three ITLAs, when its trajectory is traced backward, originates from a direction within 9 degrees of the WOW signal's source, 9 degrees on the celestial sphere. The probability of an interstellar object arriving within 9 degrees of any specific point is approximately 0.6%, or 1 in 167. This is not impossible. The sky presents countless directions. However, when considered in conjunction with all other anomalies, it represents another data point that does not align cleanly with the hypothesis of random arrival. Lowe has been judicious in avoiding overstating this connection, repeatedly asserting that the WOW signal was almost certainly not directly from 3ITLAs. The signal was detected 48 years ago, and 3ITLAs was considerably farther away at that time. If the object were transmitting radio waves with sufficient strength to be detected across interstellar distances, we would have detected the signal multiple times by now from various telescopes. The fact that we have not suggests either it was not transmitting, it ceased transmitting, or the signal was a singular event. However, the directional coincidence is intriguing. If 3ITLAs originated from a system in that particular region of the galaxy, and if that system harbored a technological civilization, and if that civilization dispatched both a radio beacon and a physical probe towards neighboring stars, then arriving from the same direction would be logical. This is not proof, nor even strong evidence, but rather an interesting alignment that raises questions worthy of investigation. Anomaly 7. L-band without iron. Spectroscopy conducted in July and August revealed strong nickel emission lines in the coma. Nickel, the element with atomic number 28, not nickel compounds or nickel alloyed with other metals, but pure nickel vapor detected at a distance exceeding 4 astronomical units from the Sun, where temperatures should be far too low for metal sublimation. Furthermore, the abundance was high, significantly exceeding that of iron, which is typically about 20 times more abundant than nickel in cosmic material. 3ITLAs exhibited abundant nickel but very little iron. The ratio was inverted, contrary to expectations. Comet experts have proposed that perhaps the nickel is bound within volatile molecules, like nickel tetracarbonyl, which sublimes at lower temperatures. However, this remains a speculative explanation, unconfirmed by observation, and it necessitates unusual chemical processes that are not fully understood. Anomaly 8. Rapid brightening. Photometric data from stereo and GOES documented a brightness increase with heliocentric distance raised to the power of -7.5. Oort cloud comets typically display exponents between 2 and 4. Exponents exceeding 6 are exceedingly rare. The scientific paper explicitly states that the reason for this rapid brightening remains unclear and significantly exceeds typical behavior. It is conceivable that the object possesses unusual volatile content, an atypical structure, or peculiar thermal properties. While possible, this has not yet been substantiated. It represents another anomaly requiring ad hoc explanations. Anomaly 9, non-gravitational acceleration. A 4 arcsecond positional shift indicating measurable thrust and momentum, requiring billions of tons of ejected gas. We have already discussed this in detail. It is a documented phenomenon, and it serves as the capstone of the anomaly stack, elevating the situation from merely interesting to urgently significant. Now let us multiply the probabilities, though not literally, as some of these anomalies may be correlated. If the object possesses an unusual composition, that could account for both the high nickel abundance and the water depletion. If it is structurally robust, that could explain both its considerable mass and its survival through the heating experienced at perihelion. One cannot simply multiply independent probabilities if the events are not independent. However, even accounting for correlations and even employing generous estimates, the cumulative probability remains exceedingly small. Low's calculation yields less than 1 part in 10 to the 16th, or 1 in 10 quadrillion. This represents the odds that all 9 of these characteristics would manifest together in a single natural object originating from interstellar space. To provide perspective, there are approximately 10 to the 11th stars in our galaxy, which is 100 billion stars. If every star released a single cosmic artifact during its existence, and these objects were scattered randomly, the likelihood of encountering one exhibiting all 9 anomalies associated with the object catalogued as 3i Atlas within our immediate vicinity would be practically non-existent. Such an object would more plausibly be discovered across numerous galaxies rather than within our own solar system, especially within a mere 5 years of initiating our search for celestial travelers. Does this definitively establish 3i Atlas as an artificial construct? No. Probabilistic arguments alone do not constitute proof. Events with exceptionally low probabilities occur with regularity. Consider the myriad of coin flip sequences. Each specific arrangement is astronomically improbable before the flips begin, yet one such sequence must inevitably manifest. Similarly, lottery winners exist despite insurmountable odds. Rare occurrences are precisely that. Rare, not impossible. However, probability arguments are invaluable for directing our focus. When a cluster of low probability events appears, when multiple independent peculiarities converge on a single entity, that phenomenon constitutes a signal. It may be mere noise or a coincidental alignment, but it warrants serious investigation, not outright dismissal. The 9 anomalies are not concealed. They are publicly available, documented, and accessible for scrutiny. The raw observational data resides in archives, the analytical calculations are published in scientific papers, and the reasoning is transparent. Should errors exist, other researchers can identify, report, and publish corrections, which is the fundamental process of scientific inquiry. Claims are rigorously examined, mistakes are identified, and flawed reasoning is exposed. To date, the documented anomalies have withstood critical review. Explanations have been proposed for some individual anomalies. Perhaps the alignment of its trajectory is simply a matter of chance. Possibly the presence of nickel originates from tetracarbonyl. It is conceivable that its rapid brightening is attributable to a composition predominantly of carbon dioxide, transitioning to one rich in water ice as temperatures escalate. Each anomaly, when examined in isolation, can be explained by a combination of unusual, yet not impossible, circumstances. Nevertheless, their collective presence renders the cumulative improbability increasingly difficult to disregard. Each proposed explanation represents a unique case, requiring the invocation of rare conditions for every anomaly. At a certain threshold, the sheer accumulation of improbable circumstances becomes less tenable than an alternative hypothesis. This alternative posits that these are not disparate coincidences, but rather interconnected attributes of an object whose fundamental nature has been misidentified. Dr. Amir Lowe developed a quantitative framework for assessing this, a scale ranging from 0 to 10, where 0 signifies a definitively natural origin and 10 indicates a definitively technological source. This scale integrates diverse lines of evidence, weighing them according to their reliability and significance to produce a score reflecting the consistency of the observations with each hypothesis. 3. iAtlas registers a score of 4 on this scale, falling squarely in the ambiguous and uncertain middle ground, precluding the dismissal of either possibility based on current information. Scores below 5 favor the natural hypothesis, while scores above 5 lend credence to the technological one. A score of 4 represents a critical juncture. One or two additional anomalies or stronger validation of existing ones could elevate this score. Conversely, the discovery of natural explanations encompassing multiple anomalies simultaneously could lower it. This scale is not without its imperfections and does not constitute definitive proof, but rather a methodology for approaching the problem quantitatively, moving beyond intuition or rhetorical persuasion. At present, this framework indicates uncertainty. More data is imperative. This brings us back to the observations scheduled for November and December. The enigmatic mass deficit cloud, the post-perihelion readings, and its close proximity to Earth. Every subsequent piece of data collected will either bolster the natural hypothesis by revealing conventional explanations for the anomalies or support the alternative by demonstrating their persistence and intensification under examination. The connection to the WOW signal represents the most speculative anomaly in the compilation. It is easily discounted. A 9-degree segment of the sky encompasses a vast area containing thousands of stars. While the probability of any given interstellar object originating from this region is low, it is not infinitesimally small. Furthermore, there is no conclusive evidence linking the WOW signal to an intelligent transmission. It could have been a malfunction, interference, or an unknown natural astrophysical phenomenon. Yet it persists because the WOW signal was singular. Across 50 years of SETI observations, encompassing millions of stars and detecting billions of signals, nothing else has borne a similar resemblance. Its distinct combination of narrow bandwidth, high intensity, and a celestial origin consistent with an extraterrestrial source remains unmatched. The majority of SETI detections are swiftly identified as originating from satellites, radar systems, or terrestrial broadcasts. The WOW signal, however, did not fit these categories and remains unassigned. If 3i Atlas is a natural object, then any directional correlation is merely a coincidence. It could have originated from any of numerous directions, and its apparent alignment with the WOW signal's origin is happenstance. Given the immensity of the universe, coincidences are not uncommon. However, if 3i Atlas is not natural, this correlation becomes intriguing, not definitive proof, but a potential hint that the WOW signal and the object might be interconnected. Perhaps the signal served as a beacon, part of a larger network, or something entirely different but emanating from the same source. Alternatively, the object could be artificial and entirely unrelated to the WOW signal. These are separate questions. Radio telescopes are currently monitoring 3i Atlas. Dr. Lowe has publicly confirmed that observers have been requested to search for transmissions. If the object is broadcasting on radio wavelengths, detection is highly probable given the extraordinary sensitivity of modern telescope arrays. Even a faint signal would be discernible. Should such a transmission be detected, exhibiting patterns undeniably indicative of intelligent origin rather than natural phenomena, then the anomaly stack becomes secondary. This would constitute direct evidence, shifting the focus from the anomalies to the immediate reality of receiving a message from a technological artifact not of human manufacture. Nevertheless, this remains speculative and driven by wishful thinking. A more probable scenario involves continued silence. No radio signals, no laser emissions, no unambiguous technological signatures, only the accumulation of 9 anomalies awaiting explanations that do not necessitate the invocation of special circumstances for each individual feature. The data will ultimately provide the resolution. November 4th marks the initial observations by JUICE, followed by ground-based telescopes in mid-November, and culminating with observations by Hubble and Webb on December 19th. Each observational phase will either substantiate the anomalies or resolve them, influencing the low-scale score in either direction. Currently, the score stands at 4, representing an ambiguous and uncertain state, the most accurate assessment based on present knowledge. Within a few weeks, more definitive insights are expected, potentially substantial. The aggregation of anomalies is a tangible phenomenon, and their cumulative probability has been calculated. The central question has evolved from whether 3I Atlas is anomalous to whether this strangeness signifies an unprecedented natural event or something else entirely, something we have long sought, ever since contemplating our solitude in the cosmos. December 19th signifies the closest approach of 3I Atlas to Earth, a distance of 269 million kilometers, approximately 1.8 astronomical units, comparable to the separation between Earth and Mars when they are on opposite sides of their orbits. While distant by terrestrial standards, it is sufficiently close for virtually every major telescope, both terrestrial and orbital, to achieve a clear observational perspective. 6 days prior to Christmas, Avibe posed a deliberately provocative question. Will 3I Atlas dispatch numerous probes towards Earth as Christmas presents for humanity? He is not asserting a prediction or claiming high likelihood, but rather raising a scenario that becomes plausible if the object is not natural, if its perihelion passage represented a deliberate maneuvering opportunity, and if its trajectory was intentionally designed rather than random. The physics governing the deployment of microprobes is straightforward. If 3I Atlas functions as a mothership carrying smaller craft or instruments, the optimal time for their release would be during perihelion. The profound gravitational pull of the Sun offers significant energetic advantages. A minor velocity adjustment applied at perihelion can result in a substantial trajectory alteration later on. This allows for the aiming of probes towards various planets and destinations throughout the solar system, utilizing the Sun's gravity to bend their paths into desired configurations. Earth, with its detectable biosignatures, oxygen in the atmosphere, surface water, the spectral signature of chlorophyll in reflected light, and radio emissions from our technological civilization, stands out as a prime target for investigation. Releasing a probe from 3I Atlas towards Earth during perihelion would require minimal thrust. The object's perihelion distance was 1.36 astronomical units, while Earth's orbit is at 1 astronomical unit. This difference is small. A velocity change of a few hundred meters per second could redirect a probe from 3I Atlas's hyperbolic trajectory to intersect Earth's orbital path at a later time. 51 days would elapse between perihelion and December 19th. During this period, traveling at an average velocity of tens of kilometers per second, a small probe could traverse the distance from 3I Atlas's perihelion point to Earth, not with ease, but feasibly. The timing is indeed propitious. Dr. Lowe is not claiming this will occur, but rather suggesting it as a scenario warranting monitoring. The Galileo project operates 3 observatories situated in Harvard, Colorado, and California, each equipped with cameras and sensors designed to detect anomalous objects within Earth's atmosphere and near-Earth space. These instruments are calibrated, automated, and continuously collect data, flagging any entities that deviate from the patterns of known aircraft, satellites, meteors, or astronomical objects. If multiple probes arrive in December, entering Earth's vicinity and exhibiting discernible activity, such as maneuvering or transmitting, the Galileo observatories might detect them. This approach focuses on systematic monitoring rather than attempting to scan the entire sky, which would be unfeasible with only 3 ground-based stations in the hope that any unusual occurrences fall within their fields of view. The December 19th close approach holds significance for additional reasons. This date represents the optimal opportunity for ground-based telescopes to conduct detailed observations of 3I Atlas. Although the object will be receding from the Sun along its hyperbolic trajectory, it will remain sufficiently close to Earth for large telescopes to resolve surface features, measure photometry, and acquire high signal-to-noise ratio spectra. The Hubble Space Telescope has already been allocated observation time, with its cameras capable of imaging 3I Atlas at a resolution sufficient to discern its nucleus, quantify its coma's size, and detect any fragmentation or asymmetries. The Wide Field Camera 3 can capture spectra across a range from ultraviolet to near-infrared, encompassing wavelengths where gas emission lines appear. Dust scattering is dominant, and the comet's color and composition are revealed. The James Webb Space Telescope will also conduct observations. Its substantial 6.5-meter mirror and infrared sensitivity will enable it to penetrate dust clouds that often obscure optical observations. The Near-Infrared Spectrograph, NIR-SPEC instrument, can analyze the molecular composition of the coma, identifying individual chemical species, quantifying their abundances, and comparing these ratios to those of solar system comets and theoretical interstellar chemistry models. Any deviations from standard cometary composition will be detected by NR-SPEC. Ground-based observatories worldwide will participate. The International Asteroid Warning Network, IAWN, has coordinated a campaign running from November 27th through January 27th, encompassing the December 19th close approach. Numerous observatories, both professional and amateur, utilizing instruments ranging from small backyard telescopes to 10-meter giants like Keck and the Very Large Telescope, will track 3I Atlas, precisely measure its position, record its brightness, and gather as much data as possible. This endeavor is framed as planetary defense training. ION treats every approaching object as a practical exercise, a chance to hone the coordination and communication protocols essential for responding to a genuine threat. 3. I-Atlas itself does not pose a threat, as its trajectory will not intersect Earth's orbit. However, it presents a valuable opportunity, a rare interstellar visitor observable for an extended period, serving as a test case for the global astronomical community's response to anomalous objects. Astrometric measurements will be crucial. Precise positional data obtained from multiple observatories over several nights will enable JPL to refine the object's orbit with exceptional accuracy. Any deviations from a purely gravitational path will become evident. If 3I Atlas has maneuvered post-perihelion, if the non-gravitational acceleration has persisted or changed direction, the astrometry will reveal it. Trajectory modifications cannot remain hidden when hundreds of precise measurements are accumulated over weeks. Furthermore, if the trajectory exhibits sustained acceleration, consistent thrust, or deviations correlating with specific events or times, this would indicate active control, an adjustment of its path rather than passive response to solar heating. While natural outgassing can generate thrust, it is typically erratic, variable, and dependent on local surface conditions. Controlled thrust, conversely, is smooth, predictable, and directional. Astrometry will differentiate between these possibilities. December 19th also represents a pivotal moment for brightness measurements. If 3I Atlas is a comet that lost billions of tons of mass during perihelion, its brightness should be declining rapidly as it moves away from the Sun. As the sublimation rate decreases with distance, the coma disperses and dust settles. Active comets typically fade after perihelion, sometimes dramatically, as the energy driving their activity diminishes. However, if its brightness plateaus, remains higher than predicted, or fades more slowly than models anticipate, this would be anomalous, consistent with an internal light source. This internal source would not need to be powerful, merely sufficient to offset the expected decline and maintain a brightness level exceeding that of a passively reflective object. Chronograph data has already indicated blue-shifted light emission rather than simple reflection. If this observation continues post-perihelion, and if Webb, Hubble, and ground-based spectrographs detect gas emission lines at intensities not correlated with distance from the Sun, this would support the hypothesis of activity driven by a source other than solar flux. Conversely, if 3I Atlas fades rapidly, its coma dissipates, and its spectra show a declining gas production consistent with cooling as the object recedes. This would lend credence to the natural comet hypothesis. Comets eventually cease activity when near-surface volatile materials are depleted, and the remaining ice becomes buried under a layer of dust and refractory material, rendering the object inert, a dark, depleted mass drifting through space. The outcome will become clear by the end of December. Observations are scheduled, and the data will be acquired. Upon its arrival, the debate will transition from speculation to evidence-based analysis. Dr. Lowe's comment regarding Christmas gifts is deliberately provocative, intended to stimulate consideration of the full spectrum of possibilities. If 3I Atlas is a mothership that released probes at perihelion, where would these probes go? What would their actions be, and how would we detect them? The straightforward answer is that we do not know. We have no prior encounters with extraterrestrial technology, thus lacking an empirical basis for predicting its appearance, behavior, or detectable signatures. Our reasoning must rely on fundamental principles of physics and the constraints governing all material objects, irrespective of their origin. A maneuvering probe in space requires propulsion, which in turn necessitates energy and reaction mass, or an equivalent such as solar sails harnessing photon pressure. For a small probe, perhaps a few meters or less, optical detection might be challenging unless it is in close proximity. However, if it is actively maneuvering, changing velocity, it might generate exhaust, heat, or electromagnetic emissions detectable by telescopes and radar systems if they are precisely targeted. The Galileo project is not the sole entity engaged in monitoring. The U.S. Space Force operates a space surveillance network that tracks objects in Earth orbit and near-Earth space, cataloging satellites, debris, and any object posing a collision risk. If a small probe were to enter lunar space, the region between Earth and the Moon, the space surveillance network might detect it, depending on its size, reflectivity, and trajectory. However, detection does not equate to identification. Numerous small objects are detected regularly, most of which are identified as space debris, fragments of defunct satellites, rocket stages, or remnants of collisions. Distinguishing a natural meteoroid from human-made debris or a hypothetical alien probe would require detailed analysis of its trajectory, light curve, and radar return characteristics. If something anomalous appears in December, something that does not conform to existing catalogs, it will undoubtedly attract attention and be tracked. If it exhibits controlled motion, maneuvering in ways that preclude natural or human origin, then the answer will be known, and the Christmas question will be resolved in the most dramatic fashion imaginable. However, this remains a less probable scenario, one that presumes 3I Atlas is not merely unusual but actively engaged in exploration. The more likely outcome is that December 19th will pass without incident. Hubble and Webb will gather their data. Ground-based telescopes will record positions and brightness, and 3-Eye Atlas will continue on its trajectory, behaving as comets typically do, offering no clear evidence of anything beyond natural phenomena. This would be the expected, uneventful outcome, confirming our current understanding of interstellar objects and allowing for a collective sigh of relief, secure in the knowledge that the universe is primarily composed of rocks and ice, not spacecraft and probes. Regardless of whether it is exciting or mundane, expected or unexpected, the observations will proceed, the data will be collected, and by the end of December, by Christmas, we will possess answers. Not complete answers, perhaps not definitive proof either way, but sufficient data to shift the probabilities, to adjust the low-scale score based on actual measurements rather than conjecture. December 19th, 51 days post-perihelion, marks the closest approach, the moment when Earth has its most favorable opportunity to observe the third recorded interstellar visitor. It is also, potentially, the moment we ascertain if we have been observing a visitor in a more profound sense of the word. The Christmas question is not whether 3-Eye Atlas will deliver gifts, but rather whether we are psychologically prepared for whatever answer the data reveals. Are we willing to embrace the evidence, even if it contradicts our preconceived notions? Are we prepared to follow the data, irrespective of our preconceptions? Dr. Lowe believes we are. This conviction drives his persistent posing of challenging questions, his publication of papers that question conventional thinking, and his proposal of scenarios that make his colleagues uncomfortable. He maintains that science thrives on fearlessness, on confronting the universe without apprehension, and on acknowledging the possibility that nature may be far more peculiar than we currently imagine. Professor Brian Cox advocates for caution, which explains his counter-arguments, his characterization of speculation as drill, and his emphasis on naturalistic explanations. He believes science functions optimally when disciplined, demanding robust evidence before accepting extraordinary assertions and protecting the public from false hope and misleading narratives. Both individuals are fundamentally driven by a pursuit of truth. Both parties aim to unravel the mysteries of Oumuamua, yet they differ on the best approach. December 19th will serve as a critical juncture, validating one of the two perspectives. The forthcoming data will either support the cautious viewpoint by revealing commonplace explanations for the observed peculiarities, or champion the inquisitive one by demonstrating the persistence and escalation of these anomalies. Regardless of the outcome, our progress will be marked by enhanced insight, diminished uncertainty, and a clearer comprehension. 50 days, that's all the time we have. 50 days until the closest observed approach. 50 days until the collective gaze of our telescopes converges on Oumuamua, meticulously gathering every available photon. 50 days until we ascertain whether the Christmas question is merely a rhetorical flourish or a genuine possibility demanding serious consideration. Meanwhile, as we anticipate, Oumuamua continues its relentless journey, accelerating away from the sun at a speed of 61 kilometers per second. It carries with it whatever secrets it may hold, traversing outward towards Jupiter's orbit and eventually beyond. It remains oblivious to our deliberations, indifferent to our inquiries, merely continuing its journey through the vast, star-strewn darkness, a path it has followed for millennia. Chapter 8. The Political Entanglement. A high-resolution image of Oumuamua exists, unseen by the public. This remarkable photograph was captured by the most advanced camera ever dispatched to Mars, precisely at the opportune moment when the interstellar visitor passed within 29 million kilometers of the red planet. The sophisticated imager aboard NASA's Mars Reconnaissance Orbiter achieved a pixel resolution of 30 kilometers, implying that this single image could resolve some of the most fiercely debated questions regarding the object's true nature. This photograph is real. It was taken on October 2nd, 2025. As of today, October 31st, 2025, it remains inaccessible, withheld from the scientific community and the general populace. The reason? A government shutdown initiated on October 1st, on that very same day that Oumuamua made its closest pass by Mars. The United States federal government found itself without appropriated funds. NASA, along with a majority of federal agencies, entered what governmental officials term a lapse in appropriations. Non-essential personnel were instructed to remain at home. The dissemination of data was halted. Consequently, the team responsible for the high-resolution imagery, despite successfully capturing what could be the most significant astronomical photograph of the decade, was rendered incapable of sharing their findings with the world. This situation is not as it should be. Scientific endeavors, particularly those involving time-sensitive observations of celestial bodies that we'll never revisit, should not be compromised by political gridlock. Yet, here we stand, witnessing how partisan budget disputes in Washington prevent astronomers from accessing data that could provide answers to fundamental questions about an object from beyond our solar system. The irony is almost too profound to fully comprehend. We possess the image. The spacecraft performed flawlessly. The camera operated with perfect precision. However, due to an unforeseen political complication in American governance, the data effectively ceases to exist. Avi Loeb, never one to remain silent when he perceives science to be under threat, has been outspoken about this predicament. He considers it utterly unacceptable that vital observational data could be withheld during such a fleeting window of opportunity. Oumuamua will not return. This represents our sole chance for a detailed study. And while lawmakers engage in debates over spending bills and shutdown deadlines, the object continues its celestial voyage, progressively distancing itself from Earth with each passing day, becoming fainter, more elusive to observation, and gradually receding back into the cosmic void from which it emerged. Enter Congresswoman Anna Paulina Luna. The representative for Florida's 13th Congressional District has emerged as an unexpected advocate for transparency in the Oumuamua investigation. Loeb conferred directly with her, briefing her on the object's anomalous characteristics and the critical necessity for the high-resolution imaging data. Luna responded by dispatching a formal communique to Sean Duffy, NASA's acting administrator, strongly urging the agency to promptly release the images. Furthermore, she advocated for the consideration of employing the Juno spacecraft, currently orbiting Jupiter, to observe Oumuamua during its anticipated flyby in March 2026. Luna's involvement is noteworthy as it signifies a rare instance of a member of Congress taking a direct and active interest in astronomical research, especially research that intersects with questions pertaining to extraterrestrial technology. Her correspondence acknowledged the significance of the data and implored NASA to prioritize its release, notwithstanding the administrative hurdles imposed by the shutdown. This served as a clear signal, indicating that at least some elected officials recognized the stakes involved. However, Luna's efforts also underscore a more profound issue: the fact that congressional intervention is required to release standard scientific data exposes the inherent fragility of our systems. We are inclined to view space exploration as an endeavor transcending political machinations, a pure pursuit of knowledge immune to partisan squabbles. Nevertheless, the reality is that every undertaking by NASA is contingent upon federal funding, federal employees, and the federal bureaucratic structure. When this framework falters, even for a brief period, the repercussions extend throughout the entire scientific enterprise. The timing of the government shutdown could scarcely have been worse. October 1st marked not merely another date on the calendar, but the commencement of the fiscal year, the pivotal moment when government funding requires renewal to ensure continued agency operations. Congress had months to finalize a budget. They were fully aware of the impending deadline. Yet, in a manner that has become depressingly commonplace in American politics, they failed to reach a consensus in a timely fashion. The government shuttered, and with it, the vital flow of scientific data came to an abrupt standstill. NASA personnel responsible for managing the high-resolution camera, processing the raw imagery, and preparing it for public dissemination were furloughed. They were instructed to await further instructions until Congress resolved the government funding issue. This is standard protocol during shutdowns. Non-essential functions are suspended, with only mission-critical operations continuing. However, a perplexing question emerges, one that no one seems able to answer satisfactorily. How can the release of data concerning an interstellar object not be considered mission-critical? Oumuamua represents an unparalleled scientific opportunity. It is only the third confirmed interstellar visitor ever detected by humanity. It exhibits numerous anomalies that challenge our current understanding of cometary behavior, and it is presently traversing our solar system at a time when we have spacecraft strategically positioned for observation. If there ever was a moment to prioritize the expedited release of data, this is it. Yet, the bureaucratic machinery of government operates according to its own internal logic, seemingly oblivious to astronomical urgency. Loeb has deliberately avoided attributing the delay to malevolence or conspiracy. He does not believe NASA is intentionally withholding the high-resolution images because they contain startling or inexplicable revelations. His assessment is simpler and, in some respects, more disheartening. Incompetence, not conspiracy. Bureaucratic inertia, not a cover-up. The system's failure stems not from individuals attempting to conceal the truth, but from the system itself being inadequately designed to manage such circumstances. Nevertheless, this distinction, while important, does little to alleviate the frustration of the situation. Whether the delay is a consequence of conspiracy or inefficiency, the outcome remains identical. Scientists are denied access to crucial data. The public is precluded from viewing images that could potentially resolve ongoing scientific debates. And with each passing day, future observations become increasingly challenging. As Oumuamua recedes into the distance, the high-resolution image holds particular significance due to what it might reveal about the object's internal structure. With a resolution of 30 kilometers per pixel, we could potentially discern whether Oumuamua is a singular, cohesive entity or a collection of smaller fragments bound by weak gravitational forces. We might be able to quantify the brightness of individual pixels, thereby yielding more precise estimations of the object's surface area and albedo. We could investigate asymmetries in the coma, detect subtle indications of jetting activity, or observe evidence of rotation or tumbling. All such information is vital. It is crucial for determining whether Oumuamua is a natural comet, as the majority of scientists surmise, or something more extraordinary. It is essential for comprehending the formation and evolutionary processes of interstellar objects. And it is indispensable for planning future observational campaigns, both for this particular object and for others that are certain to follow. The Vera C. Rubin Observatory in Chile is projected to discover new interstellar visitors on a monthly basis once it achieves full operational status. Each discovery will present a fleeting opportunity. We must develop improved protocols for rapid data dissemination, enhance interagency coordination, and better safeguard time-sensitive scientific endeavors from political disruption. Loeb's proposed solution is straightforward. Establish explicit protocols that designate certain categories of astronomical observations as high priority, mandating their expedited release irrespective of government shutdowns or budgetary crises. It should be established policy that data pertaining to interstellar objects be shared immediately, within hours or days of acquisition, rather than weeks or months later following bureaucratic review. These events should be treated as what they are, rare and invaluable opportunities to study visitors from beyond our solar system. Would such a policy resolve all issues? No. There will always be valid justifications for delays, such as equipment malfunctions, data corruption, or the necessity for calibration and validation. Scientific rigor cannot be unduly accelerated without compromising quality. However, a significant distinction exists between meticulous scientific scrutiny and administrative paralysis. Presently, we are experiencing the latter, a situation that is unacceptable. The political dimension of Oumuamua extends beyond the immediate issue of the high-resolution imagery. Broader questions arise concerning our preparedness to handle discoveries that might bear implications for extraterrestrial intelligence. Should an object be definitively identified as technological rather than natural, how would such information be disseminated? Who would be responsible for the announcement? Are there any established protocols, however rudimentary, for managing public communication regarding such a discovery? The answer is disquieting. There are no formal protocols. The SETI, Search for Extraterrestrial Intelligence, community adheres to a set of guidelines, initially formulated in the 1980s and periodically updated, outlining how researchers should approach potential detections of alien signals. However, these guidelines are voluntary, not legally binding. Moreover, they do not specifically address the scenario of discovering alien technology within our solar system. To state it plainly, we are improvising. This lack of preparation creates fertile ground for confusion, miscommunication, and potentially widespread alarm. If NASA or another space agency were to uncover evidence of extraterrestrial technology, they would face immense pressure to release this information promptly, while simultaneously needing to meticulously verify their findings before making any public declarations. The inherent tension between transparency and accuracy would be colossal. Furthermore, in the current political climate, characterized by diminished public trust in institutions and the rapid proliferation of conspiracy theories online, managing such an announcement would be exceptionally challenging. The Oumuamua situation, even in the absence of confirmed evidence of technology, offers a preview of these very difficulties. Loeb's public pronouncements regarding the object's anomalies have garnered considerable media attention and public fascination. Some individuals are energized by the possibility that we might be observing alien technology. Others remain skeptical, viewing Loeb as attention-seeking or prone to sensationalism. The scientific community is divided, with some researchers supporting Loeb's call for a thorough investigation, while others dismiss his concerns as exaggerated. Within this intricate environment, the added complication of a government shutdown and delayed data release creates a recipe for speculation and distrust. If NASA appears to be withholding information, even for reasons of ordinary bureaucratic inefficiency, it fuels narratives of cover-ups and concealed knowledge. The longer the delay persists, the more individuals will question what NASA might be concealing. And while the likely explanation is mundane, typical governmental inefficiency, the appearance of secrecy inflicts genuine damage on public confidence. Luna's intervention offers a degree of assistance. Her willingness to publicly advocate for data release signals that governmental oversight exists, that elected officials are attentive and demanding transparency. However, it also highlights the extent to which scientific progress has become reliant on individual champions within the government. What happens if Luna shifts her focus to other matters? What if future interstellar visitors arrive during periods when no member of Congress demonstrates a particular interest in astronomy? Will we simply accept that crucial data might go unexamined? The underlying structural issue extends beyond any single shutdown or any individual object. We have constructed a scientific infrastructure heavily dependent on federal funding and federal institutions, rendering it vulnerable to political disruption. While private enterprises and international collaborations can help bridge certain gaps, They cannot replicate the scale and coordination provided by governmental agencies. SpaceX can launch telescopes, but it cannot compel data sharing across multiple observatories. The European Space Agency can fund missions, but it cannot obligate NASA to expedite information release. Consequently, we are left with an uncomfortable verity. The most significant astronomical discovery of the decade might be stored on a hard drive somewhere at the University of Arizona, the location of the high-resolution imaging science experiment HiRISE Operations Center, yet remain inaccessible because Congress failed to pass a budget on time. And even when the shutdown eventually concludes, as it invariably will, there is no assurance that the lessons learned will translate into preventing similar disruptions during future shutdowns. Loeb contends that this situation necessitates change, advocating for systemic reform not solely for Oumuamua, but for all subsequent interstellar visitors. He argues that scientific data pertaining to objects originating from beyond our solar system should be treated with exceptional urgency, shielded from conventional bureaucratic delays. Is he correct? Almost certainly. Will any tangible change occur? That remains to be seen. The political dimension of Oumuamua is less captivating than its scientific enigmas. It involves no equations to solve or observations to analyze, but rather the exasperating tedium of navigating dysfunctional institutions. Nevertheless, it is equally important, as sophisticated telescopes and brilliant scientists are rendered inconsequential if the data they generate cannot be disseminated in a timely manner. And if we cannot manage this situation effectively for Oumuamua, what hope do we harbor for addressing the subsequent interstellar visitor, or the one after that, or for detecting the first genuine signal from an alien civilization? These are not hypothetical concerns. Interstellar objects are regularly traversing our solar system. Our recent ability to detect them is a testament to improvements in telescope sensitivity. Previously, our instruments lacked the necessary capabilities. However, as our observational prowess advances, we will inevitably detect more such objects, potentially dozens per year, particularly with facilities like the Vera C. Rubin Observatory. Each discovery will present a finite window of opportunity, measured in weeks or months. If our current systems cannot adapt, if we remain incapacitated by political discord and bureaucratic stagnation, we will forfeit these opportunities. We will stand by helplessly as visitors from distant star systems pass us by, unexamined, their secrets remaining veiled simply because we were too disorganized to investigate. The high-rise image will eventually be made public. The government shutdown will end, funding will be reinstated, and the data will become accessible. However, the delay itself constitutes a failure, a preventable failure that illuminates systemic weaknesses we can no longer afford to overlook. Oumuamua is imparting numerous lessons. Some pertain to astrophysics and cometary behavior. Yet, one of the most crucial lessons has no direct connection to science itself. It concerns politics, bureaucracy, and the precarious infrastructure that facilitates scientific discovery, and it is a lesson we urgently need to absorb. Chapter 9. Juno's Final Opportunity. A spacecraft is currently orbiting Jupiter, a mission that was never intended to intersect with the narrative of Oumuamua. Juno was launched from Cape Canaveral in August 2011 with a precisely defined objective: to study Jupiter's composition, map its gravitational and magnetic fields, and delve into the mysteries of the solar system's colossal planet. For over a decade, Juno has diligently pursued this mission. Following a highly elliptical orbit, it swoops close to Jupiter's cloud tops before retreating to safer distances, accumulating data that has profoundly reshaped our understanding of gas giants. Juno's mission was slated for completion in September 2025. The plan was straightforward: After years of valuable scientific contributions, the spacecraft was to be deliberately steered into Jupiter's atmosphere, incinerating itself to eliminate any possibility of contaminating Europa or other potentially habitable moons. This represented a noble end for a spacecraft that had served humanity admirably. However, the subsequent discovery of Oumuamua unexpectedly presented Juno with a novel opportunity. On March 16, 2026, Oumuamua is projected to pass within 53.6 million kilometers of Jupiter. Astronomically speaking, this is a relatively close proximity, sufficiently near for a spacecraft already orbiting Jupiter to potentially be redirected to intercept the interstellar visitor's trajectory. Avi Loeb, in collaboration with Adam Hibbert and Adam Crowell, has been meticulously analyzing the complex maneuvers required. The calculations are daunting but not insurmountable. Juno would need to perform what is termed a Jupiter-Obath maneuver. This involves two precisely timed engine gyrations. The first, scheduled for September 9, 2025, would lower Juno's perihove, the point of closest approach to Jupiter, 8 days prior to the spacecraft's originally planned descent into oblivion. The second maneuver would occur at this adjusted perihove, utilizing Jupiter's immense gravitational pull to slingshot Juno onto an intercept course with Oumuamua. The total required change in velocity, known as delta V, is 2.6755 kilometers per second. This represents a significant demand on Juno's fuel reserves. The spacecraft has been operational for over 14 years. Its primary engine has not been utilized since 2016, when concerns regarding the tank pressurization system prompted NASA to cancel planned maneuvers. Attempting to ignite it now carries substantial risks. The engine might fail to function, or worse, it could experience a catastrophic failure, prematurely terminating the mission. However, if successful, if the engine fires flawlessly and Juno can reach Oumuamua, the scientific rewards would be extraordinary. A close flyby, potentially as near as 27 million kilometers, with instruments designed for planetary science reoriented towards an interstellar visitor. No telescope on Earth or in Earth orbit could achieve such proximity, not by a considerable margin. What might Juno observe? What data could it gather that ground-based observatories cannot? Let us begin with the fundamental instruments. Juno is equipped with a visible light camera named JunoCam. Primarily incorporated for public engagement, it allows individuals to witness Jupiter's swirling cloud patterns in spectacular detail. However, JunoCam could photograph Oumuamua from a distance measured in tens of millions of kilometers rather than hundreds of millions. This translates to higher resolution, sharper detail, and the capacity to discern structures and features invisible from Earth. Furthermore, Juno possesses the Jovian Infrared Auroral Mapper, GIRAM, a spectrometer designed to analyze infrared light emitted or reflected by celestial bodies, thereby mapping their temperature and composition. When applied to Oumuamua, GIRAM could detect heat signatures emanating from the nucleus, map the distribution of volatile compounds within the coma, and identify specific molecules that are challenging or impossible to observe from Earth. If the object is experiencing heating from internal processes rather than solely solar radiation, GIRAM might be capable of detecting such an anomaly. Juno's magnetometer, engineered to study Jupiter's formidable magnetic field, could be repurposed to search for any magnetic signature originating from Oumuamua. Natural comets typically lack their own magnetic fields. They are essentially inert chunks of ice and rock. However, if Oumuamua were indeed technological in nature, containing metallic components or operational electrical systems, a detectable magnetic anomaly might be present. Although it's a long shot, the magnetometer would possess enough sensitivity to detect it. The microwave radiometer, or MWR, penetrates below the surface by gauging thermal radiation across various light frequencies. For Jupiter, this capability allows scientists to peer through its cloud formations and chart temperatures at differing depths. Regarding 3I Oumuamua, the MWR could potentially differentiate between a solid core and a chaotic collection of debris, or between densely packed material and loosely aggregated fragments. It could furnish insights into its internal structure that no optical telescope can access. Juno's gravity science instrument analyzes minute shifts in the spacecraft's velocity to map gravitational fields. This data was vital for comprehending Jupiter's internal mass distribution and could be similarly applied to 3I Oumuamua. Even a remote flyby could establish parameters for the object's overall mass. Should the gravity readings indicate a mass that contradicts its observable size and activity, that outcome would be highly significant, indeed remarkably so. The energetic particle detector and the radio and plasma wave sensor could scan for any unusual particle emissions or electromagnetic signals. If 3I Oumuamua were outgassing in a typical fashion, these instruments would register the distinct signature of ionized molecules interacting with the solar wind. However, if artificial radio transmissions were present, even faint ones, Juno might be capable of picking them up. The likelihood is slim, yet the instruments are present and would be actively listening. Finally, Juno's ultraviolet spectrograph could scrutinize the composition of gases surrounding 3I Oumuamua with a precision far exceeding what is achievable from Earth. Ultraviolet spectroscopy reveals fine details about molecular arrangements, quantities, and temperatures. It could either confirm or dispute assertions about water content, identify trace elements, and provide a comprehensive chemical inventory of the expelled material. All this data, acquired from millions of kilometers closer than any terrestrial observatory, would represent the most thorough examination of an interstellar object ever undertaken. It would not necessitate the construction of a new spacecraft or the initiation of a specialized mission. It would simply require NASA's approval of the maneuver, confirmation of Juno's engine's continued functionality, and the execution of the required burns with the agency's characteristic precision. So, why has this not yet materialized? The impediments are a blend of technical and political challenges. On the technical front, there is genuine doubt regarding the continued operational status of Juno's propulsion system. The primary engine was engineered for deep space adjustments during its transit phase and for achieving Jupiter orbit insertion. Post-insertion, it was intended for periodic use to refine Juno's orbital path. However, pressurization issues encountered in 2016 compelled mission planners to forego these adjustments. The spacecraft has since maintained its original science orbit, utilizing its smaller reaction control thrusters for orientation adjustments while leaving the main engine dormant. Can an engine that has remained inactive for 9 years still function? Perhaps, perhaps not. Engineers have scrutinized the telemetry data and believe there is a reasonable prospect of success, but reasonable falls short of certainty. Furthermore, should the engine fail to ignite, or worse, experience a catastrophic failure, Juno would be lost. Not at the conclusion of its planned mission after years of successful scientific endeavors, but during a perilous attempt to intercept an interstellar comet. Such an outcome would be perceived unfavorably, inviting criticism from those who believe NASA should adhere to its core objectives rather than pursuing speculative opportunities. Politically, extending Juno's mission necessitates funding. The spacecraft's operational period was slated to conclude in September 2025, aligning with the expiration of its approved budget. Congressional appropriations operate on specific timelines, with missions receiving funding for defined durations. Upon the cessation of these periods, funding ceases, and the mission concludes. Extending Juno's operation to March 2026 and beyond would mandate additional financial resources, increased oversight, and further justification to Congress. This is where Anapolina Luna's correspondence becomes pertinent once more, by formally suggesting that NASA investigate the utilization of Juno for observing 3I Oumuamua. Luna provided a political rationale for mission extension. She offered NASA a basis for requesting supplementary funding, a justification extending beyond merely prolonging a successful mission's lifespan. However, letters from Congress do not equate to direct appropriations. They signal endorsement but do not automatically translate into budget allocations. There is also the consideration of mission priorities. NASA manages numerous spacecraft throughout the solar system and beyond. Every dollar allocated to extending Juno represents a dollar diverted from other potential projects. Other missions, different priorities, and other scientists who have their own compelling justifications for requiring resources. The agency must balance competing demands, distribute limited funds, and provide justifications for every decision to oversight committees. Opting to redirect Juno toward 3 Oumuamua signifies a choice to forego other potential activities. This calculation is inherently complex. Avi Loeb, unsurprisingly, views the decision as straightforward. The scientific value derived from a Juno flyby vastly outweighs the associated risks and expenditures. Interstellar objects are infrequent occurrences. 3I Oumuamua could be 7 billion years old, a pristine sample from the Milky Way's thick disk, carrying information about galactic evolution unobtainable through any other means. Juno is already in position, operational, and its costs have already been incurred. Utilizing it to study 3I Oumuamua is not a new mission but an opportunistic extension of an existing one. The required velocity change is within the spacecraft's theoretical capabilities. The observation window is clearly defined. Everything appears to align. However, Loeb is a scientist, not an administrator. He can champion the flyby, author papers detailing trajectory calculations, communicate with Congress, and generate public interest. What he cannot do is make NASA's decisions on their behalf. That authority rests with the agency's leadership, who must weigh scientific potential against operational risks, balance the interests of various stakeholders, and navigate bureaucratic and political constraints. As of this date, October 31st, 2025, NASA has not officially sanctioned the Juno maneuver. The designated window for the initial burn, September 9th, has yet to be confirmed. Time is rapidly diminishing. With each passing day that elapses without a decision, executing the opportunity becomes more challenging. Spacecraft trajectories are not infinitely adaptable. Each maneuver has an optimal timing. Should that optimal moment be missed, the required change in velocity increases, the risks multiply, and the probabilities of success diminish. The September 9th date holds significance for another reason. It falls merely 8 days prior to Juno's originally scheduled termination date. If NASA approves the 3I Oumuamua flyby, it implicitly signifies that the spacecraft will not be deorbited as planned. They would be committing to an extended mission, and if the engine fails to ignite or any mishap occurs, they would face the burden of explaining why they jeopardized Juno in pursuit of what critics might label a futile endeavor. However, here lies the counter-argument, the one persistently advanced by Loeb and others. If we do not attempt it, we will learn nothing. 3I Oumuamua will pass Jupiter in March 2026, irrespective of whether Juno observes it. It will continue its journey out of the solar system, never to return, carrying with it whatever secrets it may hold. This represents our sole opportunity to study this object up close with a spacecraft. If we let this chance slip away due to excessive risk aversion or undue bureaucratic limitations, what does that communicate about our priorities? What does it convey about humanity's inclination to pursue knowledge even when it demands courage and adaptability? The March 16th flyby is not solely about 3I Oumuamua. It is about establishing a precedent for future encounters. Over the coming decades, we will encounter more interstellar visitors. Some will pass closer to Earth, others farther away. Some will be detected months in advance, affording us time to plan dedicated missions. Others will appear with minimal warning, presenting only brief windows for observation. How we address the situation with 3i Oumuamua will dictate our approach to those future visitors. If we successfully redirect Juno, if the spacecraft gathers valuable data, and if we demonstrate that existing missions can be adapted to study interstellar objects, that sets a powerful precedent. It illustrates that we are agile, opportunistic, and willing to seize unexpected chances as they arise. Conversely, if we fail to act, if bureaucratic caution and a disinclination towards risk prevent us from even attempting the observation, that too establishes a precedent. It signals that our space program is rigid, reluctant, or unable to adapt to new discoveries, more concerned with avoiding failure than with achieving groundbreaking scientific advancements. The Juno decision is also consequential due to what might occur at perihelion. If 3 Oumuamua exhibits unusual behavior when obscured by the sun, such as maneuvering, releasing probes, or displaying characteristics unexplainable by natural phenomena, the March flyby gains even greater criticality. It would present our opportunity to collect definitive data on an object that has already demonstrated it defies our current models. However, if nothing extraordinary transpires at perihelion and 3i Oumuamua behaves precisely like a typical comet, the March observation remains valuable for understanding the composition and structure of an ancient interstellar visitor. This is precisely what makes the decision so challenging for NASA. They are being asked to commit resources based on incomplete information. They do not yet know what will occur at perihelion. They are unaware of how active 3i Oumuamua will be in March, its brightness, or how easily observable it will be. They are being requested to assume a calculated risk, to gamble on the possibility that this object warrants the effort and expense of redirecting Juno. From a purely scientific perspective, the gamble is justifiable. The potential rewards are immense, and the costs are relatively modest. Juno was destined to conclude its mission regardless. Utilizing it for one additional endeavor, one more observation, one further contribution to human knowledge before its fiery descent into Jupiter's atmosphere appears to be the obvious choice. However, organizations like NASA do not operate solely on pure scientific logic. They function within intricate political, financial, and institutional frameworks that do not always align with what scientists deem the correct course of action. Consequently, we wait, we observe, we hope that the engine will be ignited, that Juno will be redirected, and that in March 2026 we will obtain our most comprehensive and possibly sole close examination of 3i Oumuamua. But should this not transpire, if NASA determines the risks outweigh the rewards, or if funding cannot be secured, or if some other impediment prevents the flyby, Juno will adhere to its original plan. It will complete a few more orbits of Jupiter, gathering the final fragments of data from its primary mission. Subsequently, on a date in late September, it will plunge into the planet's atmosphere, incinerating like a meteorite, its work concluded. And 3i Oumuamua will pass Jupiter in March, at a distance of 53.6 million kilometers, unobserved by any spacecraft, its mysteries preserved, drifting back into the darkness between stars, leaving behind only the questions we were too cautious to resolve. Chapter 10. The Thick Disk, Origin. Mystery. Envision an object predating Earth, predating the Sun, and by billions of years predating the entire solar system. An ancient wanderer that coalesced when the universe was young, when galaxies were still in the process of formation, when the initial generation of heavy elements was just beginning to enrich the interstellar medium. Now, Imagine that object traversing our solar system at this very moment, close enough to be studied, carrying within its very structure information about conditions that existed long before anything in our local vicinity was born. That is 3 Oumuamua, or at least that is what 3 Oumuamua might be. The evidence supporting its extraordinary age stems from trajectory analysis. When one traces the object's path backward through the galaxy, accounting for the gravitational influence of stars and the overall rotation of the Milky Way's disk, it becomes possible to estimate its origin and the duration of its journey. Matthew Hopkins of the University of Oxford, along with colleagues from the Otatai Oxford team, conducted this analysis shortly after 3i Oumuamua was discovered. Their conclusion was astonishing. 3i Oumuamua likely originated from the Milky Way's thick disk. If this is the case, its age is probably between 7 and 11 billion years, perhaps even more. It is older than any comet humanity has ever studied, older than the planetary systems we are familiar with, a genuine relic from the early epochs of galactic history. To grasp the significance of this, one must understand what the thick disk represents. Our galaxy possesses structure. It is not merely a random assortment of stars, but an organized system comprising distinct populations. The most apparent feature is the thin disk, a relatively flat region approximately 1,000 light-years thick, where the majority of the galaxy's star formation occurs. Young stars, rich in heavy elements, orbit the galactic center in roughly circular paths. The Sun resides within the thin disk, as do most of the stars visible to us at night. However, encircling and pervading the thin disk is another stellar population, the thick disk. These are older stars, metal-poor, with orbits that carry them thousands of light-years above and below the galactic plane, oscillating through the vertical dimension. These stars formed billions of years ago when the Milky Way was younger, smaller, and less chemically enriched. They represent a different era of galactic evolution, a time when conditions were vastly different from those observed in the thin disk today. 3i Oumuamua exhibits a vertical velocity component, a motion perpendicular to the galactic plane that is consistent with objects originating from the thick disk. When its trajectory is extrapolated backward, it does not remain confined to the thin disk, as would be expected for most interstellar visitors. Instead, it ventures far above and below the galactic midplane, oscillating through a considerably larger volume of space. This vertical excursion is indicative of an ancient object that has experienced gravitational interactions over billions of years, gradually accumulating the random velocity kicks that propel objects into thicker, more diffuse orbits. The implications are profound. If 3i Oumuamua is indeed a thick disk object, it formed around a star that no longer exists. Alternatively, if that star still exists, it is so distant and ancient that it would be unrecognizable compared to our Sun. Thick disk stars are metal-poor because they formed before multiple generations of supernovae had enriched the interstellar medium with heavy elements. This implies that 3i Oumuamua, if it is a comet, would have formed in a significantly different chemical environment than comets within our solar system. Comets from our solar system contain water ice, carbon dioxide, methane, ammonia, and complex organic molecules. They are products of a relatively metal-rich nebula, the cloud of gas and dust that collapsed to form the Sun and planets approximately 4.6 billion years ago. However, a comet originating from the thick disk would have formed in a much more pristine environment. It would contain less carbon, less nitrogen, and fewer of the heavy elements we commonly encounter. Primarily, it would consist of hydrogen, helium, and any oxygen capable of bonding with hydrogen to form water. This raises a pertinent question. If 3i Oumuamua is so ancient and originated from such a dissimilar environment, why does it resemble a typical comet? Why does it possess a coma and tail, release volatiles, and behave in ways familiar from studying objects within our own solar system? Should not 7 billion years of cosmic ray bombardment and micrometeorite impacts have irrevocably altered its surface? Should not the harsh conditions of interstellar space have stripped away volatile compounds, leaving behind only refractory materials? The answer may lie in our underestimation of the preservation capabilities of interstellar objects. Space is exceptionally cold, far colder than any terrestrial freezer, at 3 Kelvin, the temperature of the cosmic microwave background radiation. At this temperature, chemical reactions virtually cease. Volatiles do not sublimate. Ice remains as stable as rock. An object drifting through the galaxy, far from any stellar influence, would experience negligible heating, erosion, or degradation. It would simply exist, frozen in time for eons. Only upon entering the inner solar system and approaching the sun would 3I Oumuamua begin to warm up. Its surface would heat, volatiles would sublimate, and abruptly, after billions of years of dormancy, it would become active. It would appear as a comet because it is, in fact, a comet, albeit an astonishingly ancient one that has remained in cryogenic storage for the majority of cosmic history. However, there is a complicating factor. Recent analysis conducted by a team led by Xavier Perez Gutierrez from the Universidad de La Laguna suggests that 3I Oumuamua might not originate from the thick disk after all. They traced its trajectory backward through 4 million years of galactic history, examining every star in the solar neighborhood that could have gravitationally influenced its path, and they found no such interactions. None of the nearby stars could account for 3I Oumuamua's current trajectory. None had scattered, deflected, or ejected it. The object appears to have been traveling on its present course for an extended period, unaffected by local stellar encounters. This observation led Perez Gutierrez's team to propose an alternative origin, not the thick disk proper, but the transitional region between the thin and thick disks. This is a frontier zone where stellar populations intermingle, where ancient stars from the thick disk orbit alongside younger stars from the thin disk. In this interpretation, 3I Oumuamua remains ancient, potentially 10 billion years old, but it did not emerge from the deepest recesses of the thick disk. Instead, it came from its periphery, a location characterized by complex and poorly understood galactic evolution. This scenario might actually be more scientifically intriguing than a purely thick disk origin. The transitional region represents the nexus where the Milky Way's early history converges with its more recent evolution. Objects from this zone carry information pertaining to both eras, illuminating the processes that shaped the thick disk and those that formed the thin disk. Studying such an object provides a glimpse into galactic structure and history that is unattainable from objects born within a single population. However, this also introduces ambiguity into the age estimation. If 3I Oumuamua originates from the transitional region, its age could range from 7 billion years to 10 billion years, or anywhere in between. The uncertainty is substantial because we lack precise data on the conditions within that region or the timing of star formation there. Our estimations are based on educated conjecture derived from galactic models and statistical arguments rather than direct measurements. What we truly require is a chemical analysis. If we could determine the isotopic ratios of elements within 3I Oumuamua, measure the abundance of various molecules, and compare its composition to that of solar system comets and to theoretical predictions for primordial material, we could significantly refine its age and origin. This is precisely the kind of data the James Webb Space Telescope observations in August and December were intended to provide. However, as with numerous facets of this investigation, the data are still undergoing analysis, and the results have not yet been published, leaving us in a state of informed speculation rather than definitive knowledge. The question of age holds significance for several reasons. Firstly, it influences the probability that 3i Oumuamua might be artificial rather than natural. If it is 7 billion years old, it would have been constructed by a civilization that emerged billions of years before humanity, billions of years before Earth itself even existed. While not impossible, this is statistically less probable than an object originating from a more recent epoch. Greater age implies greater rarity, thus fewer opportunities for civilizations to have created it. Secondly, the age impacts our interpretation of the object's trajectory. An ancient celestial body would have endured eons of gravitational shifts, chance encounters with stars and nebulae, and chaotic orbital shifts. Its present trajectory through our solar system could be largely arbitrary, a consequence of countless minor deviations across cosmic time. Conversely, a more recently formed object, perhaps only a few 100 million years of age, would possess a path more directly linked to its progenitor star. Such an object's course could be mapped with greater certainty, potentially allowing for the pinpointing of its origin star system. Thirdly, the age of an object significantly impacts what can be gleaned about planetary formation and galactic development from the 3i Atlas. A comet existing for 7 billion years represents a direct sample of the cosmic ingredients present in the Milky Way during what astronomers refer to as the cosmic noon, the zenith of star formation when galaxies were at their most dynamic. This was a vastly different universe, smaller, denser, and more tumultuous. Examining material from that era provides empirical validation for theoretical frameworks concerning galactic assembly and evolution. A comet that is 10 billion years old is even more remarkable. At that point in time, 10 billion years ago, the universe itself was merely 3.7 billion years old. Galaxies were still in their nascent stages, and the Milky Way had not yet achieved its current configuration. Any planetary systems formed then would have been constructed from material that was virtually unadulterated, minimally enriched by preceding stellar generations. If the 3 Atlas possesses such an age, it transcends being a mere comet. It is an archaeological artifact from the very dawn of galactic complexity. Here, however, the implications become philosophically profound. If the 3 Atlas is billions of years old, and if intelligent life can indeed emerge around ancient stars, then it is at least plausible that this object may have encountered or been constructed by intelligences that predate humanity by unfathomable durations, not merely thousands or millions, but billions of years. These would be civilizations that could have risen, prospered, and either faded into obscurity or evolved into forms utterly unrecognizable long before our sun even ignited. This represents a less discussed iteration of the zoo hypothesis. It's not the notion that nascent civilizations like ours are under observation by contemporary alien beings, but rather the concept that we inhabit a galaxy that has been subjected to repeated colonization and recolonization over billions of years. This suggests that the Milky Way is ancient and that intelligence has emerged innumerable times throughout its history, each instance leaving behind traces, artifacts, or structures that endure long after the civilizations themselves have vanished. If this premise holds true, then the technological nature of the 3 Atlas does not necessitate its recent origin, not even a million years ago. It could be a probe from a billion years ago, an automated explorer from a long-extinct civilization still fulfilling its directives long after its creators have turned to dust. Alternatively, it might be a 10 billion-year-old remnant of some vast galactic infrastructure beyond our current comprehension, a piece of ancient engineering adrift in space because its original purpose became obsolete eons ago. While this sounds like science fiction, and indeed it likely is, the age of the 3 Atlas compels us to confront the reality that our galaxy has existed for an immense span of time, and that the history of intelligence within it may be far more extensive and intricate than we typically assume. By treating every anomalous object as necessarily recent and tied to existing civilizations, we risk imposing human temporal scales onto processes that operate on cosmic ones. This could represent a fundamental conceptual misjudgment. The mystery of the thick disk origin, therefore, extends beyond the mere provenance or age of the three Atlas. It challenges us to broaden our conceptual horizons to encompass the possibility that some of the phenomena we observe in the galaxy are not contemporary but ancient relics rather than active entities, akin to fossils rather than living organisms. And if the three Atlas is such a relic, if it truly dates back 7 or 10 billion years, then the anomalies we've been discussing take on a different character. They may not solely signify recent extraterrestrial activity, but could represent extremely ancient alien endeavors, engineering undertaken so long ago that the very notion of its originators and purpose becomes nearly inscrutable. More probably, however, they may indicate natural processes that we do not yet fully grasp, such as cometary behavior under extreme conditions or physical phenomena that manifest only in objects that have spent vast periods in interstellar space. The universe is indeed a strange place, capable of surprising us in myriad ways, and an object's age alone does not automatically qualify it as artificial. Nevertheless, the age of the three Atlas is undeniably significant. It alters the interpretive framework, compelling us to contemplate longer timescales and consider possibilities that lie beyond our usual assumptions. Ultimately, this is what imbues this object with such profound value, not its definitive origin, natural or technological, but its capacity to expand our understanding of the cosmos and our place within it. The three Atlas is demonstrating that the galaxy is older and more complex than our typically localized solar system perspective usually acknowledges. It illustrates that objects can endure for timescales that vastly exceed human civilization. It reveals that the Milky Way possesses a profound history, and fragments of that history occasionally traverse our vicinity, offering fleeting opportunities to study epochs that would otherwise remain perpetually inaccessible. Regardless of whether it is natural or technological, whether it is 7 or 10 billion years old, or whether it originated from the thick disk or the transitional zone, the three Atlas serves as a messenger from the distant past. Its message is straightforward. The galaxy you inhabit is ancient. It has witnessed events beyond your comprehension, and occasionally, with patience, vigilance, and a measure of luck, it sends forth a reminder of the vastness of what has transpired before.